Alright, so you're probably wondering if this is going to be a Minecraft video. In fact, it's not. I just wanted to show you my fancy horse. It's not fancy, but it's a horse. I started playing Minecraft like a couple of days ago. It's been a long time since I've played actually. Kind of forgot like just how much fun it could be. Okay, so yeah, this is just what I have so far. Don't ask why I have a lightning rod like just sitting right above my bed for some unknown reason. I just felt like doing it. I have a waypoint over there. It's actually a pretty nice world. I haven't really played much though, as you can probably tell. I have like a couple of things, like I call this crossbow. There has been like a pretty strange glitch though, in that I found iron before I found copper, and so for some reason I can't craft any kind of copper tools. And because iron is so scarce, at least for now, I have to use like these stone tools because I wasted all my iron. Well, I wouldn't say I wasted it, but I was like pretty interested to know like what this crossbow was about, and I ended up using my iron to make the crossbow, which is probably not the best idea. Wait, where's my horse? Hey, come back here. Let's get him back inside. But okay, yeah, so this video is actually going to be, I think, probably a lengthy one, so I guess maybe we'll just take breaks in and out if we need to. But it's going to be a review on linear algebra, certainly one of my favorite things, especially in mathematics. I have my old notebook here. Oh my god, like the handwriting is absolutely atrocious. Like I remember one time when I was in high school, my geography teacher at the time was telling me that my handwriting is like cockroach dancing on ink, which, like, you know, maybe there's some truth to that after all. But okay, I feel as though it's still legible, but certainly it's going to take a bit of deciphering. But yeah, fortunately though, I did make some digital notes, I think on the first 10 lectures or something, 10 or 11 lectures. So I think those will be helpful. I don't know if I made any mistakes in those at the time or what, but well, we'll try to see what we can garner from those. And then from, I suppose, lecture 12, the starting on like some applications of linear algebra, we'll have to do by hand. So we'll probably do from 12 to maybe 24 by hand, and yeah, we'll see how it goes. More so, this is just a video for myself really. If you're super interested in learning linear algebra, I'd recommend you just go take Gilbert Strang's 1806, right? MIT 1806. I don't think anybody's going to teach linear algebra better than Gilbert Strang, to be honest with you. Like, it's so good, right? So you can obviously just go refer to that. This is just something more so for me, really, so I can sort of test my own understanding. And I have linear algebra coming up, I think, this semester, so I just wanted to do a bit of review before the semester started, because like I have French as well. For some reason I decided to take French, and so I think that's going to actually be hogging most of my time, so I better make sure my linear algebra is in order. I was hoping the computer architecture course would be the first semester, because that would be like super easy for me, so I wouldn't really have to do anything there, but unfortunately that's like second semester, so I might have to actually do some work for first semester, which is fine. I feel like a lot better. And I wasn't so well earlier in the year, and so my grades sort of slipped a bit, but fortunately the GPA resets, so it should be fine. But alright, that's like super duper besides the point. Let's like quit out of this. Save and quit the title. Maybe we'll come back and play some Minecraft later on. And the multiplayer is like a lot of fun as well, to be honest with you. I found this pretty cool server, but like I died like in the server. I died with like diamond gear, bro. Like it was so sad. But the mobs were just terrible. Like I don't know how I fell into this crevice, and they were just coming and coming. Like there was nothing I could do. Like, oh my god. And it was so fast too. And there were like these little zombies, like, which I weren't aware were a thing. Apparently they're so fast, right? I thought I could like, you know, outmaneuver them. I could not. So I just died, and I died really quickly too. Like it took like 3 or 4 seconds, and I died. I was like, oh my god. And I could not find back where I died, unfortunately. So I kind of just stopped playing on the server. So yeah, salty about that for sure. Okay, so we'll start with the introduction. So it should be like maybe I should be able to breeze through this fairly quickly. So let's see, what did I do here? So the fundamental problem of linear algebra entails solving a system of linear equations. Okay, well, this sort of thing you would have been introduced to in high school already. I don't quite recall, like I was terrible at high school at math, I mean back in high school. Like, it was bad, okay? So, but I do remember, like, you could solve, like, with substitution, or you could solve with elimination, which I guess isn't too far from what you do here anyways. So there are two fundamental ways to look at this problem. The first way is what's known as a row picture, and the second is known as the column picture. So the row picture, I think, is what most high school kids would be familiar with. And so suppose you had the following system of linear equations. So 2x minus y equals 0, minus x plus 2y equals 3. So what you do is you convert this into matrix form, right? And so you create what's known as the augmented matrix. Well, coefficient matrix, really. Augmented means you tack on something. So we're not augmenting anything here in that sense. So you have your matrix A, so this is called a coefficient matrix, or matrix of coefficients. So if you notice, the 2 here is just the coefficient of your first term x here, the minus 1 is just the coefficient of this guy, and like the same pattern repeats itself. And vector x, so this matrix is multiplying a vector, right? And this would be your variable vector, or your unknowns in this case. So we have unknown x and unknown y, so 2 unknowns in the system, so you put them into a vector. And then another vector, so a matrix times a vector is going to give you a vector, right? And so you get your right hand side vector, and this would be the answer that you're looking for, right? So you're looking, okay, let me not spoil it. So you're graphing the system. So the solution of the system lies in the point of the intersection between these 2 points, right? And so this here would be your solution. Okay, and so that's the row picture. It's not great, to be honest with you. So then Gilbert introduces what's called the column picture. And so the column picture involves looking at the system in terms of column vectors, such that if we have a matrix multiplied by a vector, which in this case is the matrix A and vector x, okay, so we already established that, right? This is your matrix A, this is your vector x, so matrix times a vector. And then we can break it down into the form shown below. So we can literally tear out the vector and put it right next to the columns, right? And so what this is essentially saying is that we need some amount of the first vector added onto the second vector in order to produce the resultant vector. So this is the really important part. In other words, we need a linear combination of the columns, right, to produce the resultant vector. So we're taking a linear combination of the columns of A, right, and that linear combination is defined by this vector here, right, by your vector variable. So we're taking x, right, some x amount of this first column of A, right, and then we're adding it, so that's the linear combination, to some amount y of the second column of your matrix A. And so you should be familiar, I don't know if you took any like physics class in high school, but I remember they were like teaching vector addition, but I don't really know if what the curriculum is, like, or if you ever came across that. But in general, when you're adding vectors, like there's like this head to tail thing you do, where you stick one vector, the head of one vector onto the tail of the other vector, and that's how you add them, right? So if you look at this, right, the solution to this system would be you take one of this vector and 2 of this vector, and you get this, right? And you can literally see it, right? If you put 1 here and you carried out this multiplication and you added it to 2 and you carried out that multiplication, the result would be 0, 3, right? So you found the linear combination required to produce the right hand side. But then, so if you look at this here, right? So if you take one of vector A, so this is, well, my mouse is like malfunctioning here. I'm not sure, it's fine. So if you take one of this vector here, right, and then you take 2 of the other vector, you're going to get 0, 3. So you see that the resultant is here. So we took 1 of vector A, right? So vector A is 1 and 2, right? Let me double check. No, it's 2 and negative 1. Okay, yeah, that's my bad. So 2 and negative 1 because it's going down, right? And then vector B is negative 1 and 2, right? So negative 1 and then you go up 2, yep, so that's vector B. And so you take 2 of those, right? And you end up here. So the resultant vector is just 0, 3. And that's the solution you're looking for. Okay, and then you go on to do an example in 3 dimensions. Let me see if I can just put this mouse. I need to invest in a mouse pad, bro, because this is getting like ridiculous. Let me try my chessboard. Actually, I've never tried. Let me see how it. Whoa! It actually. Whoa! I'll use the chessboard as the. 1 second. I'll use the chessboard as the mouse pad because it's like so good. But I do need to buy a mouse pad because everything's like falling down here. Good. And I can like fold the chessboard in half so it doesn't like, you know, take up too much space. Okay, let me turn up this. Whoa, it's actually really hot today because, I don't know, it's just been super hot. I guess it's summer, so it makes sense. The fan is like struggling to keep me alive here today. Okay. Wow, this is like so much better. Oh my god, this is great. Alright, so I'll be using the chessboard now as my as my mouse, but I knew this was a worthwhile investment. Okay. Alright, so where were we? Right, so you're taking an example in 3 dimensions. Okay, so it's just the same thing but expanded now into 3 dimensions. You could look at the row picture, but we've already like quit on the row picture. So it's the same thing with the column picture, right? You just take linear combinations. You're searching for some linear combination of the columns of your matrix, right? If you put this into your matrix of coefficients, right, and then you look for linear combinations that produces this right-hand side, then okay, it's pretty straightforward. And I think this was a specially chosen example by Gilbert in that, what was this? Oh yes, yeah. So you take, if you look at this very carefully, right, the right-hand side is already, like, one of the columns is the right-hand side. So you can literally see, okay, we need none of this vector, none of this vector, and just one of this vector, and we would get the right-hand side. So it was like a specially chosen example. I do remember those words exactly. Okay, so lecture 2. So that's like basic introduction, right? And so now you're going on to solving systems of linear equations using Gaussian elimination. So Gaussian elimination is, so this is your augmented matrix now. So you just tack on your right-hand side B right next to your matrix of coefficients, right? So, okay, this should be fairly simple to follow so far. Okay, and so there's a no-terra program like MATLAB would calculate the matrix of coefficients first and then tack on the augmented matrix afterwards with the right-hand sides. But here we do right away, okay, for the sake of brevity. Alright, yeah, we're doing things by hand, but the way in which these programs work, these scientific programs work, it might be slightly different, but the idea is certainly the same. And so you need to pick a pivot, right? So we call these pivots. So this would be your first pivot. And here we multiplied the first row of the matrix by -3 and added it to the second row. And so this knocked out the 0 in the 2, 1 position. Okay, and notice the row below it is already 0, so we don't have to do anything further. Okay, so the objective really is to get all zeros below this pivot position here, right? So that's really all we're doing. Okay, and second pivot, so you come over here, and okay, so this is our new pivot position. And so in order to knock out the value below the second pivot, we multiplied the values in the second row by -2, okay? And then we added it to the last row. This produces the matrix U, which stands for upper triangular. So if you look at this matrix U, you can notice that it's in upper triangular form. So what this allows you to do is something called back substitution. Oh yeah, so Gaussian elimination can fail if there's a 0 in the pivot position, and you can't solve that with a row exchange. And I guess we should go over row exchanges, but I really don't need to. As I said before, take 1806. This is just like a review for me, and I wouldn't even like do this. This makes no sense to me. Maybe at the time this made sense to me, but now this doesn't make as much sense to me, because the way I would look at this, right, is as you're doing like a set of elementary operations, right? There's some matrix you're doing here. You didn't just, like, if you come back to this first step here, right, you didn't just magically get a 0 to appear here. There's a matrix that you multiplied by this guy here, right? So in order to produce that, get that combination out. So that's called your elementary matrix E. I don't know if I made notes on it later on, but I guess that's the proper way to see it. But that's the main idea of Gaussian elimination. You're trying to get zeros below these pivots, right? And then you can do back substitution. So back substitution, so you basically take your matrix of coefficients, this guy here, and you can write it out back into equation form. And if you notice, then it's like you can solve by you solve for z first, right? Because this is just like a single variable, so you can just like transpose and solve for z, right? And then once you have z, you're going to plug it up into the equation one step higher, and then you solve for y. And then once you have for y and for z, you go one step higher and you plug it into this equation, and you solve for x, and then you have your solution, right? So yeah, I think that's fairly simple to understand. Oh right, so this is what I was telling you about, so like representing your elimination steps as matrices, right? And so note that since we are dealing with row operations, the matrix has to be on the left. Oh, so there's a difference between a matrix being multiplied on the left-hand side and a matrix being multiplied on the right-hand side. So a matrix multiplying on the left-hand side, for instance, this guy here, right, is actually a row operation. It's like you've met linear combinations of columns before, right? For instance, I don't know if I can, if it's a good idea to, can I? Nope, can't do that. Highlight, maybe? Okay, well, I guess we can highlight the whole thing, but we can't draw for some reason. Well, that sucks, but it's fine. It's supposed to be like, I think it's LaTeX or something. I don't even remember how to use LaTeX, but it's not too hard, but I guess you can't draw on this anyways. So, yeah, so what I was saying, like, suppose, right, then we're multiplying these two matrices, and you're multiplying from the right, so then you can think of it as a linear combination of columns, right? So you can, like, think of this as, okay, if this was a vector, right, multiplying a matrix, you've already seen how to do that. You take, like, one of the first column, three of the second column, none of this column, right, none of the third column, and then you do the same thing for the second vector and the third vector. But if you're multiplying on the left-hand side, it's a row operation, so you're, instead of linear combination of columns, it's a linear combination of rows instead. And so that's exactly the right idea. That's why it's this elementary operation that we're doing. So you're taking one of the first row, right? None of this row, none of this row, right? If you look at this very carefully, what does that mean, right? So do you see, like, the result are, like, this is our matrix A, right? We took one of this row, so it's a row times a matrix is going to produce a row because it's a linear combination of rows, right? Same thing as a linear combination of columns, right? It's like a matrix times a column gives you a column, right? Row times a matrix gives you a row. That's, I guess, what I'm struggling to say for some reason. But okay, so one of the first row, none of the second row, none of the third row, right? So this is our resultant here. But remember what we said before was that we're trying to like reduce, we're trying to get rid of this tree here, right? We're trying to get zeros below the pivots, right? So we can do back substitution. Or we're trying to get the matrix into upper triangular form to do back substitution. And so what we need to do is take -3 of the first row, right? -3 of the first row, because if you had -3 of the first row, right, and then 1 of the second row, it's going to knock out this tree, right? Because this is going to become a -3 up here, and then when you add them together, you're going to get 0. Okay, and then none of this row comes into play. And that's exactly the combination of rows you need to produce zeros below the pivots, I think. So that's why I was saying earlier, like, but okay, it's a good introduction, but this is certainly the way I would look at it. Alright, and then you do the same thing here, right? So we need one of the first row, none of the other, so you get back the first row. And then here we need, okay, you can probably notice the identity sort of appearing here as well. Just one of the second row, none of the other, so we leave this row the same, right? So now we're working on this pivot here. We're trying to get zeros below this pivot. And so what you do is you take -2, right, of the second row, right, and you add it to the third row. So -2 of this row would give you, let's see, right, would give you -4, right, and then you add it to this row, and then you would get 5 here. So yeah, and this is how you end up with your upper triangular form. Alright. Oh, and then notice then we had 2 steps, right? We had this E21 and we had this E32, and that's the pivot positions that we're fixing, right? And so you can sort of put these two matrices together, right? And you have to do them in order as well, in the order in which you carried out the operation. And you'll see that this is actually not necessary to know, because when you're doing Gauss-Jordan, when you tack on the identity later on, you'll come to this, but when you tack on the identity, then this elementary matrix E is going to show up anyways, right? But this is how you do it. If you were to take like these steps one at a time, you'd have to multiply them out together to get like this one main operation, right? So instead of doing this like one at a time, you can have E, some capital E, right? Some matrix that sort of encodes all the operations at once that you need to produce the upper triangular matrix. And then there was a segue on permutation matrices, so it's the same thing, really. And so this permutation matrix is on the left-hand side, right? And so we just said that, like, if a matrix is on the left-hand side, it's a linear combination of rows, right? And so here you took none of the first row, right, and one of the second row. You can literally see that appearing here. Here you took one of the first row and none of the second row. And so what you've done then is permute. You did a permutation, right? And notice then that this is off the diagonals. This is like switched around, so you can like expect that's what's going to happen anyways. Okay, and alright, and this is a permutation example with the columns instead. Now the matrix, right, the permutation matrix is sitting on the right hand side, and we said, okay, well, that's going to be a linear combination of columns. So now we're taking none of the first column and one of the second column. You can see like the second column showed up here, right? And then we're taking one of the first column, none of the second column, and so you've literally just, you did a permutation, really. Okay, so fairly simple. Let's see, anything else here? All right, so it's not possible to change the order of operations. AB is not equal to BA, but you can change the order in which those operations take place by moving parentheses. Okay, yeah, that's like fairly straightforward stuff, so I think that's enough for lecture 2. Lecture 3 is this one here, multiplying matrices. But we've already met this before, right? And so, what is this, dot product? Okay, yeah, so you can do it by dot product, which I think is like probably the worst way to do it, but maybe, okay, that's a good idea to see it like this as well, because there are some proofs later on that rely on this fact. So, okay, it's a good idea. So C, right, is equal to A times B, so rows of A, columns of B, okay? I think this is like fairly straightforward what a dot product is. I don't want to like go into that. And multiplying by columns, like we just explained this, right? Okay, matrix times a column gives you a column, okay? Multiplying, what is this? Okay, linear combination. Oh, multiplying by rows, and okay, notice this time it's on the left. We literally just went over this. Column times a row. What is this? This looks like it might be a bit important. Let me get some water here. Oh, okay, so the point is a column times a row gives you a full-size matrix. Why is that though? Like, we have to understand like intuitively why we're getting a full-size matrix. Like, the way I want to look at this, right, because I don't really care about like rules and like regulations. Just like you have a set of like basic understandings that you should be able to like generalize to anything anyways. So let's see, this is a matrix here, right? We can think of this as a column, right, even though it only has one entry, right? So we're doing linear combination of columns, and so we're taking one of this entire matrix, even though the matrix is like literally just a vector. So we're taking one of this, so it's going to produce this right hand side to be an entire vector, and then okay, yeah, we take 6 of this vector and it's going to end up here. And so yes, a column times a row is going to indeed give you a full-size matrix. We have like the same logic that we've been using all the time anyway, so we don't need like any of this fancy like logic whatever was going on here. So we're good to go. Block multiplication, what was this? Oh, okay, yeah. Inverses. Okay, so the inverse of a matrix exists if when you multiply it times some matrix A, it produces the identity. Okay, well, this should be fairly straightforward. Currently, this inverse is positioned to the left and is indicative of a row operation, but it can, if it's a square matrix, it could be sitting on the right as a column operation as well. Doesn't matter. But this isn't true for rectangular matrices, so this is why square symmetric matrices tend to be like the most important classes of matrices you deal with. Anyways, okay, so a left inverse is not the same as a right inverse, and yeah, it's a shape mismatch, of course. Okay, so what if the matrix is singular or has no inverse? So notice that vectors 1 and 2 and 3 or 6 are simply multiples of each other, right? They're just multiples of each other. And so they point in the same direction, right? In other words, there's no linear combination of these vectors that exists such that when you add them together, you can produce the identity matrix. So you don't span the entire space, basically, is what's going on here. Alright, yeah. So A inverse cannot, so the matrix is singular, so you can find some non-zero vector x. So when you multiply by the matrix A, the result is 0. And A inverse would not be able to recover it, right? Because, there's like a simple proof here. If AX equals 0, right? Then A inverse times AX is equal to 0. X is equal to 0. Which is not true because there is a vector. There's a non-zero linear combination of the columns of A that produced the 0 vector, but A inverse was simply not able to recover it here. And so, okay, your conclusion is that your system is not invertible, right? Or it's a singular matrix. And here, I guess I was asking GPT for some clarification for something. For singular matrices that have no inverse, there exists some linear combination of columns that will produce a 0 vector. Now this means that one vector essentially knocks another one out. What was what was I smoking? Therefore, one linear combination of columns plus another column equals blah blah blah. Therefore, we think this is geometrical in following manner. Suppose we drew a line of symmetry along the axis. Oh god, I was like way too creative back then. What is going on? If I understand your statement correctly, you're suggesting that for singular matrices there exists a linear combination of columns that produces a 0 vector, and this implies that one vector essentially knocks out another, whatever the hell that means, right? Resulting in a linear combination of the columns plus another column equaling 0. Then you mentioned the idea of folding space along y equals 0. Oh my god. I was definitely smoking something. Okay, so let me clarify the key points. Singular matrices and linear dependence. I guess that was my misunderstanding at the time. I didn't understand this idea of dependence, yeah. It is true that for singular matrices there exists a non-trivial linear combination, of columns that result in the zero vector. This indicates that the columns are linearly dependent, okay. Okay, GPT is like straightening out things here for me. Vector knocking out another. The notion of one vector knocking out another may not be the most precise way to describe it, obviously, okay, in retrospect. But the essence is that the information carried by one column can be expressed as a combination of the others, yep. But okay, it's always good to ask like questions, right? It might seem like a stupid question to you in retrospect, but maybe at the time it's not such a stupid, I guess there's no such thing as a stupid question, right? So linear combination of columns plus another column equals 0. If a matrix is singular, you can express one column as a linear combination of the others. This can be stated as a linear equation, okay. Constants, okay, those are columns. Folding along the space y, doesn't directly relate to the linear dependence of columns in a singular matrix. The linear dependence is more about a relationship among vectors in the matrix. Oh yeah, and this is the idea of like spanning and so on, which we're going to get onto later on. So okay, so here you go to find the inverse of a matrix using Gauss-Jordan. This is what I was telling you earlier. You can just tack on the identity matrix here onto your system, right? So this is now your augmented matrix. And then you do Gaussian elimination. So you start by eliminating below the pivots, right? But then you don't stop there. You also eliminate above the pivots as well. And what this is actually going to do is your identity matrix, right, is going to keep track of all of the operations that you did. All of these elementary operations we were talking about before is going to show up here, right? So yeah, that's all your identity matrix is doing. So here we're doing just the same thing again, right? Eliminating, and here. So now we ended up with the identity here, right? And this E, right, over here. And so what you started it was E, right? To E is the elimination matrix that carries out the entire elimination process. Okay, I couldn't spell for some reason in one shot as discussed in the previous lecture. Okay. And looking at the multiplication process from the column perspective, we can tell that E times the first column of the matrix V would produce the first column of the matrix P, which is simply the identity. And okay, yeah, so E times A gives you the identity. And we know by definition, the inverse times A, for instance, has to be equal to the identity, right? And so we can deduce that E must be the inverse, right? So it's as simple as that, really. Okay, so we can move on to lecture 4, so hopefully we're making good time. Okay, transposition A equals LU. Oh, so this is just LU factorization. No, it's actually PA equals LU, because you might need to do like some permutation, like some row exchanges. Sometimes the pivot, well, we can't say zero pivot, but the pivot sitting, like a zero sitting in the pivot position, I guess would be a better way to say that. You have to do a row exchange. Okay, so that's fairly straightforward. So there's the associative property, which we've met. I remember he was given like a really funny, this guy is so funny, I'd be laughing during these lectures. What was it? Something about like taking off your socks and putting on your shoes, and then the right way to invert that process would be to what? Take off your shoes, put on your socks, right? And then the right way to invert that process would be what? To put on your socks and then put on back your shoes. Okay, something like that. It was pretty funny. Inverses of A transpose. So what is this? Here, the associative property swings into play again. Let me start at the beginning. Transposition A equals LU. So A times A inverse equals I. A inverse times A. Okay, it's the same thing. Yeah, so this is like a square matrix, so left or right. Inverse doesn't matter. Here, recall that we can change the order by which we carry out multiplication. Right, so we can't, it's not commutative, but it's associative. So I guess I need to do a bit of research into this as well. It probably doesn't form like a field in the traditional sense, but there must certainly be some set of rules by which they're governed. So okay, yeah, so you can like move the brackets around. So it does have the associative property. So if we had AB and then B inverse A, we can like do B times B inverse first, right? And this would produce the identity, and then we can do A times A inverse, and then that would produce the identity. So that makes sense. Okay, yeah, so here, that was just like a long-winded way of explaining what I just said, and then so we talked about inverses of A transpose, and so A inverse equals I, and then for some reason A times A inverse transpose is I transpose. Okay, transpose of a product is the product of the transpose. The product of the transposes in reverse order. So hence we get, okay, so the transpose of a product is a product of the transposes in reverse order. Okay, so it comes in reverse then. So you take A inverse first, and then you take A transpose, right? So A inverse transpose times A transpose should give you the identity. And so hence the inverse of A transpose is, oh, okay, yeah, A inverse transpose. Because the matrix when multiplied by A transpose will produce the identity. Oh, yeah, okay, that's fairly simple. And so we end up with A equals LU, so factorization in this case. So previously we had this general form E times A equals U, right? Okay, yeah, we just had like this elementary operation to produce the upper triangular. And here what we're doing is we're finding the inverse, right? And we're just tacking it on to this side here. So I hope you see what's going on here. So I'm multiplying this side by E inverse, right? And so A, right, is equal to, is this what's happening? Let's see, I suppose that's what's happening. And you call the L like the inverse of E in this case. Yeah, oh yeah, okay, yeah, that makes sense. So therefore we put this in the form A equals LU. It's trivial, all that needs to be done is to multiply both sides by the inverses of E, which would give A equals LU. So L is quite literally just the inverse of E. And what is E again? Okay, yeah, it's just a collection of steps that you took to get the matrix into upper triangular form, but it's not necessarily the inverse of A itself because we didn't put the matrix into reduced row echelon form. So now if you did reduced row echelon form, which is what Gauss-Jordan does, you eliminate above and below the pivots, then the E should be the inverse, right? Like if you tacked on the identity and then you go reduced row echelon form, the E should produce the inverse. And so if E is the inverse of A, then A itself should be the inverse of E, right? So you can just put A back. Could you? Or does that make no sense? Okay, yeah, I guess I'm just getting a bit ahead of myself, but I think it is a question worth asking. Okay, so here we did a example with a 3x3 system with no row exchanges. So here you have like your combination of elementary operations on A to produce upper triangular form, and then, okay, so recall in order to find the inverse of a product of matrices, we multiply them by the inverses in reverse order. And so what happened here really is that we oh, okay, yeah. So so find the inverse of the product. Oh yeah, so this was the first proof that we did, like all the way at the top, right? Yeah, so that's why. So Gilbert really does have a way with teaching, I suppose. So you multiply them by their products in reverse order, right? So E32, E31, E21, right? And then you multiply by in reverse order. And remember, you can do this associative property thing. So E21 times E21 inverse would produce the identity, and this times this would produce the identity, and then E32 by E32 inverse would produce the identity. You're left with A, right? And then just these three elementary operations together to give you like L, so A equals LU. And then, okay, there was like a bit on the computational cost of elimination, and okay, this was a pretty interesting part of the matrix. So, not the matrix, the lecture. So, okay, I'll refer to that half of lecture 4 for a clearer explanation. Can't spell, obviously. Maybe I can just like correct these. Clearer explanation. Can't spell explanation here. Okay, and then he did a bit more on permutation matrices. Yeah, we already know like these are needed to do like row exchanges. So we know P inverse is P transpose. Okay, yeah, P transpose P is I. Oh yeah, that makes sense. Okay, so lecture 5. So we're moving along now. So far, so good. Lecture 5. Where's lecture 5? Do I have lecture 5? Oh, here it is. Transposes, permutation, and spaces Rn. Okay, what was this about again? Okay, the previous lecture we had discussed elimination in form A equals LU. However, the actual form is PA equals LU. Ah, yes, I remember this because you might actually need some permutation of A if you had like a 0 in the pivot position. And so we talked about transposes here. Suppose we had some matrix, like I remember a joking like there's no mathematics that went on here, like we just got a matrix that was standing up to lie down, which is funny. So essentially your rows turn into columns, or your columns turn into rows. Okay, columns turning into rows is probably a better way to see this. Okay, but it doesn't matter. How you want to look at it is fine. So you have this column and it turned into your row, and you have this column and it turned into a row. And the transpose of a matrix, so this is the formal definition, is defined such that row I and column J of the transpose matrix comes from row J and column I of the original matrix, such that A transpose IJ is A J I. And that makes sense. You can like see it right here. And so then I guess we spoke a bit about symmetric matrices. And so in essence, when you are transposing a symmetric matrix, so A transpose A, there's no change because you're folding the elements across the main diagonal. Yeah, that makes sense. And you can see it like right here, like and these are like the most important classes of matrices. And later on you'll learn about like positive definite matrices and so on. Okay, so A transpose A is always symmetric, and this can easily be proved by taking the transpose of this product. Recall the rule for multiplying transposes, and so A transpose, you take it in the reverse order, so this would be A transpose transpose is A transpose A, so it's the same thing. Okay, yeah, that makes sense. So here A transpose just cancels out to A because carrying out the operation twice is like the same thing. So yeah, you get back to the starting point. So now we talked about vector spaces. So a vector space allows you to take a linear combination of vectors such that you can scale and add them together. Well, that's quite literally the definition of a linear combination. An example, let me put in that L, of a vector space, for instance, would be R2, which simply represents a two-dimensional xy plane. Okay, R2 is all two-dimensional real numbers, fair enough. It's important to note that vector spaces are closed under addition and multiplication, so there's closure. So is it a group? It might be a group, right? There's closure, there's associativity. I'll have to go over like the exact rules that govern these spaces. And if some linear combination of vectors or multiplication by some scalar moves the space in question, then it cannot be considered a vector space. Well, that makes sense. Take, for instance, the upper right quadrant of this Cartesian plane. Would this be considered a vector space? The answer is no, because suppose we had some, we get outside of the space, we multiply by a scalar quantity -3, this would take us outside the vector space. As such, it's not closed under multiplication and addition. Makes sense. Okay, subspaces. A subspace is essentially a vector space within another vector space. For instance, within the vector space R2, there exist the following subspaces. So R2, okay, so the vector space itself is considered a subspace. There's the null space, so the 0, 0 vector is the smallest subspace, and any line through the origin is also considered a subspace. I see. It's important that the line must pass through the origin for it to be considered a subspace, as the 0 vector has to be included to keep the system closed. Otherwise, you wouldn't be able to multiply, for instance, by the scalar 0. Therefore, the origin itself is very fundamental to subspaces. Yeah, that makes sense. And so now we talk about the column space, which we've already been talking about columns a lot. And so, where do these subspaces come from? So matrices, recall that we can encode information into matrices and look at them as vectors. Column vectors being the preferred choice here. So if we have the following matrix, okay, first of all, we can see that the column vectors of this matrix belong to the space R3. Why is it R3? Okay, well, yeah, the vectors have 3 components, right? So it's R3. In order to form a subspace, we need to be able to take a linear combination of those columns, okay, such that they never leave the space. The name given to this space is the column space. So all linear combination of these two vectors will produce the column space, right? Yeah, okay, and it's obviously through the origin. So that makes sense. So let's go over to lecture 6. Column space and null space of a matrix. You have a vector space when you can add vectors or multiply vectors in such a way that v plus w and cv stay within the space. In other words, all linear combination of the vectors stay within the space and can be represented as cv plus dw. Alright, subspaces. A subspace is a vector space within another vector space. Recall that R3, okay, they're the following. Okay, so R3 itself, right, there's a plane through the origin. Oh, right, so here we're trying to get like all of the subspaces inside of R3. So it's R3 itself. Okay, we mentioned that the 0 vector a line through the origin, which would be the null space, right? And a plane through the origin as well. Yes, well that makes sense. Okay, the union of two subspaces. Suppose that we took all vectors in the plane or the line or both, that would form a subspace. The answer in this particular case is no. Suppose you have some vector from the plane. Okay, so you have a vector in a plane, you tried adding it to a vector on the line, there's a very good chance you end up outside of the union. Okay, so it's not a subspace. So okay, you can't take the union of two separate subspaces, for instance, even in R3, and end up with another subspace. The intersection of a plane and a line for any P and L will always form a subspace. Okay, yeah, well that makes sense, because the line is in the plane, so yeah, it makes sense. Okay, column space of A. Let's see. Column space of A is a subspace of R4. Okay, four components, and in order to find out what this column space is, you need to take all linear combination of columns of A and see what they will fill out. And then this is the idea of independence, basis, and span, right? Or we're not there as yet. Alright, so now we're asking, does AX equals B? Does it always have a solution for every right-hand side B? If so, what are those solutions? If not, then what right-hand side B's are okay? So in this particular instance, no, because we have four equations, right? We have four equations, 1, 2, 3, 4. So we have four rows then, and three unknowns in this particular case. And so we would not be able to get, like, there's no way that we can find all right-hand side B's with just three vectors here, or like a vector in R3 then, right? So your solution space is in R4, but the vector space here is only in R3, so that's a problem. So let me see what nodes I have here. So you can see that we need to find three unknowns, x1, x2, x3, but there are in fact four equations that make up the matrix. Hence, it's already quite clear that in fact it's not possible to get all right-hand sides B in such a case. However, there exists right-hand sides B that do have a solution, yes, of course. If the vector B happens to match with the columns of the matrix, then you simply take one combination of the set column and none of the others to produce the result. Right, fair enough. Okay, so AX equals B can be solved exactly when the right-hand side B is a vector in the column space. Okay, right. Okay, and recall that a column space contains all linear combination AX, therefore those are the only possible solutions that can exist for B. Well, that makes sense. Okay, so null space now. So contains all solutions x to the equation AX equals 0. So you're trying to find linear combinations of the columns of A that produce the 0 vector. Hence, the question we're really asking here is, okay, yeah, well, I just said that. And this can also be represented as this. Okay, so all linear combinations now. So you can have a basis for your null space, right? And then like there's an entire line then. If there's something in your null space, right, depending on the dimension of your null space as well. But like if your null space was like one-dimensional, right, there's an entire line of vectors, right? You have a basis for the space, and then like any combination, like any stretching factor, if you want to think of it that way, on that line will solve the equation. Okay. Yeah, fair enough. Okay, when checking to see if a vector space is formed, check to ensure the 0 vector is included. Okay, so lecture 7. Alright, so finally we get to solving AX equals 0. Alright, so you have to solve for the null space first, because you need the null space to solve for AX equals B. And so the algorithm to solve this system, where we're looking for all possible combinations of vector x to solve the system AX equals 0, that is to say all vectors are multiplied by the matrix of systems of equations, A will produce a linear combination of the column vectors that result in the 0 vector. Okay, fair enough. So we start off with a matrix of coefficients A, and we're trying to find all linear combinations that solve AX equals 0. And so you just do elimination, right? So you found your first pivot here, and then you eliminated before. But this is a pretty instructive example, because you noticed here, right, then that there's no way, there's a 0 sitting in the pivot position, and then there's no way to escape with a row exchange, right? Can you see that? So what do? We just go over to the next column to find the next pivot, right? And then you eliminate below that pivot as well, and then this is your system here. And then you couldn't proceed further, right? Because there's like a 0 sitting in the pivot position here, and there's no way to do like a row exchange that's going to like fix this. So you're done. You're basically done at this point. Okay. So so you can notice here then, right, then we have a row of zeros, which means, right, that there was some combination of the rows, right, of this matrix that produced the zero row, and so it's singular, right? That's how you know. So that means all of the rows, right, inside of your row space, if you want to think of it like that, or your column space, even if the row space is like dependent, if you want to call it that, it means that the column space is also dependent as well. So there's also some linear combination of the columns of this original matrix that produces, like, it doesn't contribute anything new. Can we find, you can see it's like this middle column right here. Can you see it, like it's the same vector, or just, is it the same vector? Maybe not. Let's see, but somehow we know that the columns they're dependent on each other. The question is, like, what, you just have to find like the right scalar amount here. Maybe it doesn't, like, there's like a neat whole number, but certainly we can see that the rows are dependent, and you can see that because the first row, if you add the first row and the second row together, you're going to get the third row. So quite clearly the rows are dependent, but not so obvious for the columns. Okay, and so then you end up with this system here in upper triangular form, and the number of pivots in the U matrix tells us the rank of the matrix. Okay, so this is a very important point, right? So once you take your matrix into upper triangular form, the number of pivots that you are able to find is a rank of your matrix. Rank is pretty important. So the columns where the pivots are located are known as the pivot columns, and the remaining columns are called the free columns. So if you notice, we have 2 pivot columns and 2 free columns, right? When solving ux equals 0, the insight here is to take any value whatsoever for the free columns. They don't matter, but for simplicity's sake, we're going to take, you set 1 to 0 and you set the other one to 1. And then you can, like, solve via back substitution for the pivot variables and obtain a solution. Okay. So first off, let's begin by writing out your equations, right? So you turn your matrix back into a equation form, right? And then you solve. Okay? And since you have 2 free columns, you're going to need to find 2 vectors, right? So your null space is actually 2-dimensional. So we have here, what you do is you solve for x1 and x3. So you're solving for the pivot columns, right? And notice that we start by setting the last free variable to 0, right? And you set the other one to 1 in this particular case. And then you solve, okay? So this would allow you to solve via back substitution. Yeah, and we can, like, easily, like, figure out this is -2, and this linear combination is going to give us a 0 vector. And so the algorithm continues, so you check the other possibility as well, right? And so you set, so you set this guy to 1, and you set this guy to 0, and then you solve. Excuse me, and then you solve, and you get this here. And so the same goes for this as well, but we solve for a single vector. We can't extend in any direction by multiplying by any scalar, therefore we found another line. Hence, it can be concluded that the null space in this instance is a 2-dimensional plane in R3, which I said before, right? Going through the origin. So in other words, null space contains all linear combinations of all the special solutions. Special solutions arise when you permute all the free columns in order to solve via back substitution. And okay, the system of equations to obtain. Okay, that makes no sense, but alright. what did I have? The special solutions arise when you permute the free columns in order to solve via back substitution. Okay, the system of equations to obtain the solution to the pivot variables. Okay, that sentence somehow makes no sense to me, but okay, the idea is there. You do Gaussian elimination, you take your matrix into upper triangular form, you identify your pivots, and then you just set your free variables to 0. For instance, the last one, you set the other one to 1, and then you can solve the system one at a time. And so that's, like, completely fine. And in this particular case, we had 2 free variables, like 2 free columns, right? And that's how come we ended up with, like, an entire plane, right? And it's like a 2-dimensional space inside of the entire subspace. So it's just like two lines, really. Okay. Yeah, and all linear combinations of these 2 lines would give you a plane. Yeah, so it's a plane in R3. Okay, and then we did reduce row echelon form. Okay, so this is the one like I'm more familiar with. Like you do okay, so you do above and below the pivots, and you're gonna end up with this here, this system here, and it's pretty nice because now, right, the solution that you get, if you look at this very carefully, the identity matrix is showing up here where your pivots are, right? And then in your free columns, the solutions, you can read them off like directly. You can just read off the solutions. Like if you look at this very carefully, right? But you have to invert them though. So if this is a 2, right, it'll be -2, right? If you notice -2 here, and then 0, and then this would be 2 and 0, and this would be the basis for your null space. And so the form in general is this guy here, -f, so negative the free columns, and then you tack on your identity. Okay, and then that's fairly simple. And then we did an example with A transpose, and okay, fairly simple stuff here. And then you get like the entire basis here for the null space. So that's pretty good. Lecture 8. Now you solve AX equals B. And I think I'm gonna take a bit of a break. I need some water, so I'll just have to pause the video. Where's the mouse is giving trouble, so my chessboard now is not doing me so much favors anymore. Maybe I need to like dry it. Yeah, there's a bit of water like on it. Yeah, I think that was the problem. So let's just pause this recording and I'll be right back. Okay, so we're back. I think. I'm not sure. I'll have to pause this again because I'm not certain if the video split or if it's just like, no, it definitely split. That's terrible. Yeah. Okay, well, if that's the case, I think I'll have to find a way to like splice them together or something. I don't know. But okay, I guess we'll just continue anyways. So yeah, we're at solving AX equals B, row reduced form R. Okay, so you do like your typical elimination, and yeah, you're gonna end up with this here, and condition on the solvability of B. So B is solvable exactly when some vector lies in the column space of A. We've already discussed this. Or in other words, it's some linear combination of the columns of A. Okay, we already know all of this, and so now we're just looking at an example, right? And so the equations from this matrix are as follows, and so we've put this into, this is an upper triangular form. And to solve this system, a good technique is to set the free variables to 0 and solve for the pivot variables in order to obtain a particular solution to the system. So you're trying to find for x particular. Oh yeah, I remember this. And okay, and so you set your free variables to 0, right? And so you have x1 and x3. And so you're solving then for x1, x3 in this particular case, and that's a particular solution. And so then you can do via back substitution. This is fairly simple, and you'll find, okay, somehow this back substitution, let me just spell this properly. Okay. And yeah, this is what you're going to get when you do back substitution here. You're going to get -2, 0, 0, and 3/2, and this is in fact a solution, a particular solution to this now. So we have to find all of the solutions to the system though, not just one particular solution. So what you do is you add all the vectors found in the null space to the particular solution. And so the complete solution is x particular plus the null space. Well, I guess all linear combination of your null space bases. And so we know AXP equals B, and we also know the matrix A times any vector in the null space gives 0, so AXN equals 0. Therefore, AXP plus XN equals B plus 0. It's like a little trick that goes on here. Notice that adding the null space will give the complete solution because any linear combination of vectors in the null space always brings us back to the 0 vector. Okay, by definition, right? Therefore, the solution on the right-hand side is always the same. So we can add the entire null space to our x particular vector and multiply by the matrix A, and the result B will still be valid. So this operation is akin to translating the entire null space. This instance, the null space has 2 free variables in it, and therefore we got a plane. So the entire plane through the origin is translated by whatever the x particular vector was. And okay, if you notice, it's the same example we did the last time where we found a null space. And so here, the complete solution would be the x particular plus all linear combinations of the null space basis. And this is like what it looks like, I guess. Yeah, well, yeah, exactly what it looks like actually. All right, and so now consider an m by n matrix of rank r. And so we know that the rank is less than or equal to m. M by n, m is rows, right? N is columns, and rank is less than or equal to n. So it's less than or equal to the rows, less than or equal to the columns, obviously. So yeah, the rank of the matrix can never exceed the size of the matrix itself. And so the first thing you talk about is full rank matrices. Full column rank simply means r equals n, right? In this particular case, there means there are no free variables, right? So yeah, that means like there's a pivot variable in every column, right? Right, so the null space of the matrix will be the zero vector only. And so there's only one unique solution if it exists, and that would be the x particular. So if you can find an x particular, then that would be the only solution to the system, because the null space is just the zero vector only, right? So the complete solution is the particular solution if it exists, right? All linear combination of the null space basis. In this case, the null space is just zero. So yeah, you just end up with an x particular solution. And oh right, and here we had an example. You put this into reduced row echelon form. This is what you end up with. And you can tell right away by looking at this matrix that two of the systems of rows don't contribute anything new and reduces to zero. And since there are no free columns, we know that the null space is just zero vector. So only particular solution to this system would exist. Okay, so if some row is a linear combination of other rows, this will show up in the column space as well. Yeah, we were talking about this before, but it might not always be so obvious. So we just spoke about full column rank, right? Now we have to talk about full row rank. Since every row has a pivot, we know that once we perform elimination, there's going to be a pivot in every row, okay? Hence, there are no conditions on B such that every right-hand side is solvable. Oh yeah, well that makes sense. Well, this is probably like your ideal case in like full row rank, right? And yeah, this is what you end up with here. Okay, and then you talk about full rank. Okay, and these are the particularly invertible solutions, right? So the rank is like, it's full rank, basically full row rank and full column rank at the same time, and then it's invertible and there's always a solution. And then here, for rank less than n less than m, if you reduce, you're gonna get the identity here, free variable here. Oh, and like there's a row of zeros below, so there is condition on solvability here. Okay, so here are the cases summarized and what the rank of a matrix tells you about its solutions. Which lecture was this? Lecture 8. I think I might just go rewatch this lecture, speed run a 20-minute and see, just to double check. If the rank of a matrix is the same as the number of rows and columns, so the rank of the matrix is the same as the number of rows and columns, there exists a unique solution. Okay? If the matrix is full row rank, okay, and every row has a pivot, then there are no conditions on the vector x to solve the right-hand side B, since every row is contributing new information to the system. Well, that makes sense. If it's full row rank, right, that means that there's a pivot in every row, right? And then there's no, like, zero rows then. And so, but do we have free columns though? Since we have free columns at play, there are an infinite number of solutions due to the null space. Oh yes, that makes sense. So even though it might be full row rank, there might still be a column that's a free, like there's a free column there, right? There's no pivot in that particular column. But how would that happen? Let me scroll up. I need to see how this happens exactly. So full row rank in this particular case. Yes, so there's a pivot in every row here, right? But then you might end up with like multiple free columns in this particular case, right? Because the matrix is like rectangular. Yes, and that makes sense. And so there's like, yeah. So there's an infinite number of solutions, right? Because you can find a particular solution, yes, and then you can take like all linear combinations of the null space basis. So yes, that makes sense. And if the matrix is full column rank, which is okay, this means that there either exists a unique solution or no solution at all. Unique solution. Why is there a unique solution? Because the null space basis is a zero vector only, because all of the columns have pivots in them, so there are no free columns, right? Okay, well that makes sense. So there either exists a unique solution or none at all. I see. Right, so it's either just X particular or there just isn't a solution. That makes sense. Okay, lecture 9. So I think this was a short lecture. Yeah, independence, basis, and dimension. So if we had some n by n matrix, A whereby m is less than n, row by columns. In other words, there are more columns than rows. More columns than rows. Okay, then we can safely conclude that there's something more in the null space other than 0. And this was the case we were talking about 0 before, where maybe we had full row rank, right? And this becomes apparent as well if you look ahead and realize that since there are more columns than there are rows, then there will bound to be free columns that will show up in the null space. Okay? Independence. Since we had some vectors x1, x2, all the way to xn, if no linear combination other than the 0 vector, other than the 0 combination produces a 0 vector, then they're said to be independent. So if you have 3 vectors in a plane, they will automatically be considered dependent. Okay, yeah, well, that makes sense. If we were to represent this in terms of a matrix, we would see automatically that this is a case where m is less than n, okay, row is less than columns, okay, and there is a free column, which means there would exist a subspace of vectors, which when you take their linear combinations produces a 0 vector. Yep, we already discussed this. Therefore, we can automatically conclude that 3 vectors inside of a plane are not independent. In other words, there exists non-zero vector combinations to x, to the equation ax equals 0. And we've already seen why that's the case. Like, it's not invertible. Hence, we can conclude that a set of vectors in some matrix A are only dependent if the null space of said matrix is a 0 vector only. Are only dependent? Or only independent? Right, they're only independent, not dependent. Span. If we had some system of equations comprising of vectors v1 to vn, then we can say these vectors span the space if it consists of all combinations of set vectors, right? So that's the idea of a span. So you take ax, take all linear combination of the column space, and it spans the entire column space, I guess, is what we're trying to say here. So basis for a vector space. A sequence of vectors that span a space and is independent, right? This just means that you have the right number of vectors to span the space. If you had more than you needed, they wouldn't be independent. Right, exactly. It's like if you were in R2, for instance, you would only need 2 vectors to span the entirety of R2, right? You can look at this, like, if you had like a vector on the x-coordinate of your Cartesian plane and one on the y-coordinate of your Cartesian plane, and then you took all linear combinations, then you would get the entire Cartesian plane, you get the entire plane, right? But if you had one vector, you could never leave that line. And then if you had 3 vectors, then you have too many now, right? So suppose we had 3 equations, so 3 equations and 2 unknowns. In this scenario, there would be solutions or right-hand side b's that would not be able to obtain because all linear combinations of the 2 columns would yield a plane, right? So yeah, so if you had 3 equations, right, then your solution space is in R3, your column space is in R3, right? But the vector itself, the linear combinations that you're taking, is in R2, right? So you're only able to take a plane, if you look at it, you're only able to take like any 2 of those vectors. You're not able to use all 3 of them, right? So you can't span the entire 3-dimensional space. You're stuck in a plane, basically. Okay. Yeah, so it's not a sufficient basis for R3. Makes sense. You need 3 vectors to like get a basis for R3. You can use like the unit vectors if you wanted to. Anyways, the number of rows inside of the basis vector array consists of the dimension of the space. Number of rows inside the basis vector array consists of the dimension of the space. Okay. If we had, okay, all right, so we're defining dimension. If we had some system, we can tell the dimension of the basis vectors by checking the rank. Right, so the rank tells you the dimension, yeah. The rank of said matrix happens to be the dimension of its column space, and then this in turn tells us how many vectors we need to form a basis for the column space. If we had a system in R4, okay, with 2 free columns and 2 pivot columns, okay, so the column space would be 2-dimensional, right? And the rank of the matrix would be 2. Well, yes, your rank, you have 2 pivot columns, the rank is 2, and the dimension would be 2, right? Right, and so you only need 2 of those variables to construct a basis for the column space, exactly. Okay, and so the dimension of the column space is the rank of the matrix. We've already identified that. And dimension of the null space is the number of free variables involved, and that's n minus r, right? So if you had n columns, and you just subtract off the rank and you get the number of free variables. Makes sense. Lecture 10. Let's see. Is there a lecture 10? I don't know. Oh, right, the 4 fundamental subspaces. Now, this is a lecture you do have to watch, I feel like. But there's the column space, which we've already met before, right? There's a null space, which we've met before. There's the row space, which is just the transpose of the column space. And we've met the row space much earlier when I was talking about, like, instead of thinking about it as a linear combination of columns, you just think about it as a linear combination of rows instead. And that's essentially a row space. But for, like, our purposes, what we do is we just transpose the column space, right? And that's your row space. So you can think about the row space in terms of columns. And so you don't have to change anything at all from what we've been doing so far. Because everything we've done so far is like really a linear combination of columns, right? So you just transpose the row space and you get a column space. So it's a column space of A transpose. And then you have the null space of the column space of A transpose, right? And that's actually called the left null space. So, okay, that's like fairly simple. But I think I should just go through the entire lecture just to make sure I'm set, right? So let's see, the column space. The dimension of the column space can be found by checking its rank or the number of pivot variables, like we've seen that before. The basis for the column space would be the pivot columns. These serve as independent vectors that can be used to span the space. Okay, fair enough. The basis for the null space of A is simply the free columns or special solutions. Okay, n minus r is the dimension. Okay, and then we talk about the row space. The dimension of the row space is given by r. Number of pivot variables, the rank of the matrix doesn't change even if you transpose it. Well, obviously, let's suppose we had a 3 by 3 matrix at rank 2. This means there are 2 pivot columns and 1 free column. This would also mean that the rows were not contributing anything new as well. Hence, the rank of the matrix would be less than m. Even if you were to transpose the matrix, the fact wouldn't change as the rows are being eliminated. So there are. So yeah, they're just turning into columns, right? It makes sense. And then you have to find a basis for the left null space. Oh, right. And he was saying, oh, you don't have to like go through this entire procedure again. Like, what did you have to do again? I don't remember exactly. So here we just tack on the identity matrix to the original A and take it to its reduced row echelon form, and the matrix E will show up. E is akin to the inverse. Oh yes, I was making a point about this at the very beginning. E is akin to the inverse when we were solving Gauss-Jordan system. It just keeps a record of the steps we were taking to get the resultant matrix R. And so yeah, you just take your system. So you transposed, right? Did we transpose? Yeah, column space of A transpose. Tack on your identity matrix, reduce, and oh no, something's definitely wrong here. Something looks wrong here. Let's see. Tack on your identity matrix, and so what we're doing is, whoops. So my mouse is giving me trouble again. Yeah. I do need that. I really do need that mouse pad. I feel like it also doesn't help that it's like one of those really cheap mouses. So yeah, the amount of times I've dropped this thing is like crazy. Yeah, I think it might just be coming to the end of its days. Let me try putting it back on like the regular desk. Yeah, like it's not gonna work. Come on, mouse. Oh, here we go. We're back. Alright, so you augment with the identity, fair enough. And so what we're doing is we're trying to get 0 below the pivots. So, okay, minus row 1 added to row 2, which in this case, so you leave row 1 unchanged, minus row 1 added to row 2. Fine. And then minus row 1 added to row 3. So here you... Yeah, I think this is a problem here. This is not... Yeah, this is not exactly what it should be. I think you leave this unchanged, right? You leave this unchanged because minus row 1 to row 3, this is fine. How do I get the notation back? Oh my god, what is this? Yikes, man. Okay, augmented with the identity. I guess this is here, right? Yeah, this is here. This is this first matrix here. Okay, begin matrix, end matrix. So this is the first matrix. Minus 1 to row 2. And so here I said 0. What is this? 1, 1, 2, 3, 1. So this is like... But where's the... Oh, right. So this is 0. Oh my god, it's like so hard to read. I don't know what happened here. but it's like extremely difficult to read, but I should be able to. But point being, right, this is supposed to be 0, 1, 0, so let me just look for the negative one. Is it this one? Let me just hope it's this one. 0, 1, 0. Nope. Let me just undo whatever the hell I just did. Okay, so it's not this matrix, it's this matrix here. So let me try turning this into a 0. Oops. Yeah, no, this is absolutely correct. Right, so you leave the second row unchanged, and then you do -1 of row 1 to row 3. Right, and so this is correct. And then here, you do -2 of row 2, 2 of row 2 to row 1. 2 of row 2 to row 1. So you end up with this system here, but we're trying to get like zeros both above and below the pivot. So let's see what's going on here. So we got our columns of zeros here, minus row 1 to row 3. This is fine. And then now no. What I did was like certainly wrong. Because your augmented matrix, your E, is supposed to be like changing like the entire time. So something is definitely up here. Yeah, something is definitely up here. Let me check. I have like this old book. I don't know. It's supposed to have like very similar notes as well. Time to go into the book and see what we find. So this is lecture 10. So what are we doing here? I kind of forgot what we were doing. We were reducing this. Oh, we're finding a basis for the left null space, right? Lecture 10. No, I don't think I have anything here on lecture 10 actually. We skipped over this, and then I think I have from like lecture 12 onwards. So I think we're just gonna have to like figure this out the hard way. Okay, it shouldn't be like that difficult though. Like, so we augment with the identity, fair enough, right? And then we take -1 of row 1 and we add it to row 2, -1 of row 1, right? And then we take 1 of row 2, fair enough, and this produces like exactly this, right? Okay, and then we took -1 of row 1 and then we added it to row 3. Okay, -1 of row 1 and we added it to row 3. Right, and okay, that produced like a row of zeros here. And then why didn't we stop here? Because we need to eliminate both above and below the pivot. So we took 2 of row 2 and we added it to row 1. And what did we get though? Oh right, so we produced like 0 above this pivot as well. So the problem was that the value above this pivot was not quite there. So you took 2 of row 2 in this particular case, which is -1. So you took 2 of row 2 and added it to row 1, which doesn't make sense. Why is it -1 in this case? Oh right, so we're just adding upwards, right? We're adding upwards. So we also have to add the values here as well. So if you took 2 of this row, this is going to become 2, right? This is going to become 0. And then -2. So something here is like off, right? But this was a 1 previously, no? This was a 1 previously. So if you take 2 of this, yeah, it's going to be -1. So this is actually correct. Yeah, this is fine. So okay, it's a good thing like we double checked that though. It certainly looked like something was wrong. But this is why it's like good to like take practice on these things, because you might know like theoretically what you have to do, but sometimes the mechanics really do require a bit of practice. Alright, and so the point was that we see like the exact linear combination here. We see we see what we need. Like the the basis for the null space, the left null space is like sitting right here in this E matrix. And so hence we can see from this that the basis for the left null space can be found in the third row of the matrix E, and it would be one-dimensional, and that's the row that shows a linear combination of rows that can produce the zero vector. And so you can see here that then the linear combination is just this guy right here. So that's your basis for left null space. If you didn't want to do this, you could just do the same thing you've been doing anyways. You transpose your matrix, right? And then you eliminate normally, and then you would find your pivot columns, and then you would find your free columns, and then you can just use the same thing again, and you would be able to find a basis for your column space as well. So if this like made no sense to you, you can like do that perfectly fine, and you're good to go. Okay, and so I think that brings me to the end of like the first 10 lectures, and then we can go on to my notebook, which I do not promise is very helpful. Let me turn up this fan because I'm dying here right now. The fan is on like max speed. Oh my god. Like, the sun is just not it. I'm getting hungry as well. Somebody told me that the mall is closed today, which is, I don't know if that's true or not, but I'm gonna have to like figure out like how am I gonna eat. Alright, so let's open up our trusty writing application. Subtract this. Let me get some water as well. Okay, and so the next like useful lecture, I suppose, is on applications of linear algebra. So I should put this like applications. And I believe this one's lecture 12. Lecture 11 was not so useful, I don't think. Yeah, you can like watch it if you want, but there's like no real value that you're getting there that you already haven't gotten. And I think there's 11b, which was like the first quiz review. So it's definitely like helpful though to go take the quiz for yourself and see like how you did. Okay, so I think we start off with an incidence matrix and you encode a graph, right? So this is like some basic introduction to graph theory. So suppose we had a graph like this, 1, 2, 3. So we have some nodes. I think I covered like some of this stuff like in some of my tutorials, like depth first search and breadth first search kind of thing. Oh god, please mouse, don't die on me now. I need you to like last, especially for like my Minecraft playing session later. Okay, and then maybe I'll just use the touchpad. Let me see like if the touchpad is any bad. So you have this node leading into here, and by the way, we're modeling an electrical circuit in this particular example. This comes here, like this comes here. Node 3 comes to node 4, and I believe node 1 goes to node 4 as well. And then we have to label these edges. So this we can say is edge 1, this is edge 2, this is edge 3, and this is edge 4. Okay, and so the first thing you need to do is be able to construct what's called an incidence matrix. So I'll collect this. So construct an incidence matrix from a graph, right? So this is a graph, and we need to, it's a directed graph actually, and we need to construct what's known as an incidence matrix. So what is an incidence matrix? So I'll just go ahead and show you, and it should be like fairly straightforward like what that is. So the first row of our matrix would be -1, 1, and then zeros everywhere else. Okay, so it's like this, and if you look very carefully, the -1 is just saying, okay, well, we're leaving node 1 and we're going into node 2, right? From node 1, okay? And then here on this guy, this is going to be representing node 2 now. We're leaving node 2 and we're going into node 3. So we put the -1 here and we put the 1 here, like this. And then, okay, you do the same thing here. Excuse me. Right, and so for this guy here, current is leaving node 1 and it's going into node 3 as well, right? So current is leaving node 1 and it's going into node 3. And then current is also leaving node 1 and going into node 4. So you would say, okay, well, -1, leaving node 1, going into node 4, zeros everywhere else. I think I might be getting a bit hoarse, so I kind of have to hurry this up. And then, okay, finally current leaves node 3 and goes into node 4. So we have 0, 0, leaves node 3, goes into node 4. And this is our incidence matrix. And already you can see here, like, I think he made like an important point very early on in the lecture, is that you can see you already have like linearly dependent rows here. Because I think if you added these rows up together, you would get like these two rows, you add them together, right? And you get the third row. Okay, so you can tell that they're linearly dependent. And that actually corresponds to loops, right? So this is a loop and this is a loop. So we have two loops inside of this system. So that's like very important to know. Okay, and so the first question I think he asked in this lecture was, he asked about the null space of the matrix, right? And so, okay, yeah, well, there's something in the null space, obviously, right? So we know that because we've already seen then that there's like linearly dependent rows. That means, right, there's also linearly dependent columns as well. So there's something in the null space and there's something in the left null space as well. So, okay, let's see. How did I show this in my notes? Right, and then the thing inside of the null space is actually what's called constant potential. So if you took this matrix, right, and you multiply it by a constant potential, in this particular case, this would be our null space basis. So you did 1, 1, 1, 1, and 1, like this. If you actually took this particular linear combination of columns, you would get the 0 vector. Okay, so this is a basis for your null space. Completely fine, and you can check this. You can check this linear combination for yourself. And I think his example was like a little bit nicer, where you can write this system out exactly. You can write AX out, right, as like x2 minus x1, x3 minus x2, x3 minus x1, right, x4 minus x1, and then x4 minus x3, right? You can write it out like that, and you would see then like quite literally, the variables are potentials at the nodes, right, x1 to x4, and then multiplying by a, it gives you the potential difference across the edges, right? So like pretty neat stuff. So okay, what did we do from there? Oh right, so then he introduces Kirchhoff's current law. I'm not sure if I should like introduce that like right away or, but okay, there's this thing, there's A transpose Y, like you need to look at A transpose Y. I'll just like move along in the lecture. It doesn't matter if it's making sense or not right now. Like towards the end it should make a little bit of sense, but you certainly do need to like watch that lecture for yourself, because I won't be able to like go over every little nook and cranny, but I'm just doing it to make sure I sort of remember what I'm about. Okay, so A transpose Y equals 0, so you just transpose this matrix and you solve for the left null space, and you would find the rank m minus r in the dimension 5 minus 3, the dimension would be 2. Okay, that makes sense. And let's see, so now I think this maybe is the important part that I should try to remember. So if we had, I suppose I can type this. So if we had like x1, so x would be equal to what? x1 to xn, right? And we said before that this corresponds to the potential at the nodes, okay? And then we had some matrix A that is acting on this x, right? That's our unknown. So we have some matrix that's acting on this, and that's going to, A times x is going to produce a potential difference, right? So we have E, call this E. So A times x is going to produce a potential difference, and the potential difference is just like x2 minus x1, like what we had before earlier, right, in our null space. So the null space of A is the potential difference, really. So null space of A is the potential difference. Okay, and then there's some matrix C that links potential difference to current, like the current on the edges. So the current on the edges, so current on the edges correspond to like y1 to like y5 or whatever, right? y1 to yn in this case. Right, so that's the current on the edges. So there's some matrix C that links them together. And so the relationship between current and edges is Ohm's law, I believe. Yes, it's Ohm's law. What is that exactly though? So current on an edge is the same, it's like some number, right, times the potential drop. And we know like Ohm's law is like voltage is equal to current times resistance. And so that number is the conductance of the edge, right? Or it's like 1 over the resistance. So if you transpose this equation, you would get current is equal to voltage times 1 over the resistance or the conductance. Yes, that makes sense. So it's Ohm's law. Yeah, it makes sense. And so the equation, like, it's like showing you like I equals V times 1 over R, or you can just say I is equal to V over R if you want to look at it that way, right? Like, it's just showing you the relationship between current, resistance, and change in potential, really. And so now A transpose Y is, it's like a balance equation, right? This is where this is called Kirchhoff's current law, actually. And so it's, okay, he does like a really nice example. Like, okay, you transpose the matrix, right? And then remember we had before A and we saw like linearly dependent rows already, and we said, okay, it's like corresponding to like a loop inside of the system. Well, it's like very similar in Kirchhoff's current law. It's like A transpose Y equals 0. So you're solving for the left null space now. And like, it's a balance equation. You see, like, current in is current out, right? So it's really nice, actually. And so let's like put this all together. So you start off with A, right? And then you get A times X, and you get, this is how you get your potential differences, and then current is going to come from that potential difference, right? So Y, current is going to come from that potential difference. So Y is going to be equal to C times E, right? C times E. In this particular case, like, that's that matrix, right? That's that matrix C we were talking about previously. And then finally, you do A transpose Y equals 0, right? So then, you start here, come to here, start with A, AX equals E, multiply E by this guy Y, right? So that's C times E, and then you multiply that by, that's Y by A transpose to get 0, and this is going to lead you to Kirchhoff's current law. So you start with an unknown X, right? Multiply by A, this gives you the potential difference. You multiply by C, so that's like a physical constant in Ohm's law. Then you multiply by A transpose, and then you get F, right? So F would just be like an external, like a battery or something, right? If you put in a battery, because you need something to like make current move. You need to create that potential difference. And so F is just like your external current, then, current source, or a battery. And so really what you end up with is, so you start with X, right? Multiply by A, right? Multiply that by your constant C, your matrix, and then you multiply that by A transpose. So this is Kirchhoff's current law, so this is A transpose. This entire thing here is Y, and this is equal to F. And this is like the most basic equation in numerical linear algebra, really. Okay, and I think that's like the summary of this lecture, and it would be really helpful like if you went and worked like a numerical example as well. It's quite nice, really. But I think that's enough of that. Oh yeah, there was like some bit where he like talked about the derivation of Euler's formula as well, but okay, let's not get into that. You can go take MIT 1806. I'm like the MIT 1806 salesman, apparently. Okay. Alright, and then now, this is where we went on to the 90-degree chapter on orthogonal vectors and subspaces. I feel like, I'm not sure if this is like my favorite chapter, but maybe it is. I don't know. Well, actually, the chapter on eigenvectors and eigenvalues and high powers of a matrix and applications to Markov matrices and so on is also very nice. And then you get to positive definite matrices, and then you get to see Fourier series and like complex numbers come into play, and it's so nice, man. It's so nice. Like, come on. And then there's like singular value decomposition as well. All of it is nice. Okay, I don't think I can pick. I can't pick, but this is like very nice as well. Okay, so what is an orthogonal vector? So let me see if my notes do me any justice, which I doubt they will for some reason. But fortunately, you can always go like retake. Like, his videos are so well done, and you can like watch it on 2 times speed. Like, you just pick up back the information so fast. So I I'm just gonna try to use it like this. So this is a 90-degree angle here, and if we had some vector x, right, and we had some vector y, and this is the hypotenuse of your triangle here, x plus y. This is the vector x plus y, right? And so the test for orthogonality is x transpose y equals 0. Oh god. Please mouse work. Thank you. X transpose y equals 0. This is not theta 0. So this is your test for orthogonality. But like why, right? So if you had like x transpose y and you get the result equals 0, then they're orthogonal to each other. But like why is this the case? So let's use Pythagoras' theorem to prove this actually. So if you have the length squared of some vector x, oh no, the mouse stopped working again. If you have the length squared of some vector x, right? Like this. And then so it's like a squared plus b squared equals c squared basically. Had the length squared of some vector y, and then this would just be equal to like x plus y squared, right? So okay, it's gonna take some time, but you're gonna have to bear with me here because my mouse died apparently. And so we know that the length squared, right, is x transpose x, right? This is a fact. X transpose x is the length squared. And you can like test this for yourself. Like get some vector x, right? Transpose the vector and then do the multiplication on the left, like do row operation x transpose x, and you're gonna see that you're gonna get the length squared of that vector. Like if you're not convinced, and you shouldn't be convinced, you should like be checking these things for yourself. So it's x transpose x plus y transpose y. Again, we're just going at like a snail's pace apparently. It's going to be equal to x plus y transpose x plus y. Okay, so please mouse work for me. X plus y transpose x. Okay, let me try to. So the board is not helping us anymore. Plus x. Maybe like let me try to like fix the mouse. Maybe it's the problem with this little thing here. This little glass thing that's like refracting the light. Oh yeah, that like I think that was the problem. Like it keeps shifting, so yeah, the mouse feels a little bit better, but I definitely need to buy like a proper mouse, bro. Okay, x plus, oh my god, it stopped again. So we're just gonna take like slow and steady. Okie dokie, there we go. And then what you're gonna do is you're gonna expand out your right hand side, right? And you're gonna end up with x transpose x. You're gonna have to bear with me here. Plus x transpose y, and you should know how to expand this out as well, right? Just FOIL it. X transpose y plus, oh my god, y transpose x. Okay. Plus y transpose y. Yeah, I think that's it. Y transpose y. Y transpose y. And so you can actually do some cancellations now. So y transpose y is going to go with this, right? And x transpose x is going to go with this. And so you're just left with x transpose y plus y transpose x, right? And is equal to 0, obviously, because you cancel that on this side. And you can actually just write this as x transpose y. Like it's like 2x transpose y, and like it cancels out, right? So y transpose x, right? Or you can write it as x transpose y. Like it doesn't matter. It doesn't matter what order you do it in, because it's just dot product, right? At least when you're dealing with real numbers as well, the order in which you take that dot product does not matter. So you're able to say, okay, y transpose x is x transpose y, right? So that's 2x transpose y, and then let me just write it out. It's 2x transpose y, and then you just divide both sides by 2, and you're still going to end up with 0. So x transpose y equals 0 really is the test for orthogonality. Okay, hopefully you're like convinced of that at this point. Okay, and then the next thing I see here is like orthogonal subspaces, which makes sense. So every vector is orthogonal to every other vector t. So this is like the definition for like two subspaces to be orthogonal. So like every vector in subspace S, right, has to be orthogonal to every other vector in your other subspace T. That's the condition you need for both of your subspaces to be orthogonal. And this is where your 4 fundamental subspaces come into play, and I think this is like the fundamental theorem of linear algebra as well. The fact is that the row space, right, is orthogonal to the null space. Is the row space orthogonal to the null space? I'm not sure. I think it's the something to that effect. It's the column space, I think. I think the column space is orthogonal to the left null space. And yeah, and the row space is orthogonal to the null space. Yeah, that's literally what I just said. Like, the row space is orthogonal to, or like the column space of A transpose is orthogonal to the null space. So yeah, I had the right thing, but I just need to like make sure I understand. But like, why is this? Okay, so let's look at the equation AX equals 0. It's like literally encoded in the information as well, right? Like, if you had, like, look at this. This is so nice, right? This is matrix multiplication. Like, if you understand it, like, it's right there in front of you. So if you had like some matrix A, right, and don't think about the columns of the matrix, think about the rows of the matrix A instead, right? And you're multiplying some vector X, right, which is like your null space basis. Why is the row space, like, why is the row space perpendicular to the null space? Why is that? Look at this, right? You could see, like, if you took this vector here, right, and you did the dot product with this vector here, you get 0. And if you took this vector here and you did the dot product, you get 0. You took this one, you did the dot product, you get. Do you see, like? And this is what I was saying, like, very early on in the course. It was like nice to see why the dot product as well was very helpful. And this is quite literally X transpose Y equals 0, and that's our test for orthogonality, right? So X transpose Y equals 0. There it is, like. And then you can take any linear combination. So every vector inside of the row space, right, is perpendicular to your null space basis. And so that's the test for orthogonality, as we said before. I hope that's clear, you know? And so the column space and the null space of A transpose is also orthogonal. So A transpose X is equal to 0. And the column space becomes the row space in A transpose X, so we can take the same logic and apply it here as well. Like, you can go think about that if you wanted to, right? The column space, right? If you're transposing it, your column space is becoming your row space. If you transpose a matrix, think about that. You had a matrix A, you transpose it. Your column space now becomes your row space. And you do the same logic you did here, right? And you're gonna see then, okay, well then the column space has to be, you know, orthogonal to your null space. Yep. Well, to your left null space, actually. Yes, so your column spaces are orthogonal to your left null space. Alright, so then we went on to projections. So I think so far we're good to go. So next chapter is on projections. I think I should probably just like speed watch. Take like a 3 or 4 days and just like speed watch like 1806 again. Projections onto subspaces. Yeah, this is where it starts to get like really, really nice. So let's see. So you had some vector B like this, and then you had some subspace, we'll call it A, like, and then you sort of project this vector B onto your subspace like this. And then this, where it lands here, is called P. And notice then that P is some like multiple of your subspace, right? I hope you can see that. Like, P exactly here is some like somewhere along your subspace basis, right? You get like some combination, and you have to like stretch to find where this lands. So P is XA, and then you have this error vector E here sitting, and E is, what is E? E is B minus P, exactly, yeah. E is B minus P. Well, I hope you can see that. And what is P? Well, P is just B minus XA, right? P is just XA, right? So you just substitute. So this is B minus XA here. Need some water. Oh no, is my water finished? No, it's fine. Okay, yeah. All right. And I think it helps as well if you just go and do like an example to see why this error vector E really is this vector B subtracted off from your component here, right? It's really good to like see that. And it'll probably be somewhere over here as well, right? It won't be exactly here, but the length is what you're interested in really, right? Okay. And so yeah, so this is where the nice stuff comes in. Is my mouse working again? Let me check. Yeah, it's working a little bit. So we know that A transpose E, right, is equal to 0. This is like our like really key equation here. A transpose E is equal to 0. Like somehow our sense is telling us, like when we project, right, onto this subspace A, right, they have to be perpendicular to each other, right? They have to be perpendicular to each other. So A transpose E, right, has to be equal to 0. So E and this subspace must be perpendicular to each other. Like this is our reasoning here. And this is like the whole point of the entire thing. And so you can just expand out E. Like we said, E was this guy here. And so you can just say A transpose B minus XA equals 0, right? And then you can just... Oh yeah, you can do a bit of reordering here as well, but then you just like FOIL this out, right? And so this is just A transpose B. So this is just, oh god. Okay, we gotta go back to our touchpad. So A transpose B, right? So you're just multiplying out A transpose B minus X A transpose equals 0. And you can reorder X, right? This value here is a scalar. Remember, this is a scalar quantity, so it can like sit outside of the vector in any particular order. Okay, so you can move that around. In that sense, the scalar is like commutative, but the actual vectors or matrices themselves are not commutative. And then you end up with A transpose B is equal to, A transpose B. So you just do like a little bit of transposition is equal to XAA transpose. Okay, and finally we get X. So now we finally found X, right? We don't know what X is. We finally found X, and X is going to be A transpose B over A transpose A rather, A transpose B over A transpose A. A transpose, what am I saying? You divide both sides by A transpose, and you're gonna get A transpose B over A transpose. Okay, I guess I'm getting tired or something. A transpose B over A transpose, but we got this. We're gonna make it through this. Okay, we're gonna get this done in one go. All right. So finally, we made it all the way there, and so we know P, our projection matrix, is just like A times X. Like that's it, right? So it's A times this thing, right here. All right. So that's our projection matrix. And it's some quantity that's acting on B as well. And so we know that P transpose P is symmetric, and then, okay, yeah, and P squared is equal to P as well. Like if you project twice, you're gonna end up in the same place. So like all of this is clear. Yeah, so you just do like a substitution here. We found X, right? So you substitute this in, and so your projection matrix is just A, right, multiplied by whatever X is. So A transpose B over A transpose A. So you're good to go. And so like why project, right? Yeah, so this was the whole point. Why project? It's because, insert page after, because sometimes AX equals B might have no solution, right? But what you want to do is find like the best possible solution. I think in the particular lesson he gave like an example with like a satellite buzzing by, and then there's like so much noise inside of the system as well, right? You might not have like an exact solution, but you can find like the best possible solution. So instead of solving AX equal B, you're solving AX hat, so you're solving best possible AX is equal to P. I'm solving best possible, because the solution might not have like any there might not be any solution to the system at all. Okay, and then I think we sort of generalize from here into higher dimensions. I'm just like checking ahead in my notes to see. There's a numerical example, and then there's like orthogonal matrices, and then there's the Gram-Schmidt process. And then there's a numerical example on the Gram-Schmidt process. And then finally we get to properties of determinants, and I think there's like 3 lectures on that. It's like so important. And then determinant formulas and cofactors, and then mathematics for the millionaire joke. And then there was like a 4x4 numerical example I have here in my notes. And then there's like Cramer's rule, inverse matrix, and volume, which I think is very important. At least you get to see like how determinant ties into volume. And finally, my favorite chapter, I suppose. Well, not favorite, but at least the chapter that I use the most: eigenvalues and eigenvectors. And I feel like this is probably the easiest chapter to understand. And then there's like diagonalization and powers of A, and then there's like a Fibonacci example, and yeah, and then there's like Markov matrices or stochastic matrices. There's an example here. I think I had an example with, instead of the one he gave with population, I had an example with economics instead, but it's fine. You can even use it in robotics. Like there's plenty, endless applications to Markov matrices, really. Oh my god! So I really don't know if I'll be able to cover to cover all of this, but I'll do my best. So where were we? Numerical example? No, yeah. So okay. I might need another break pretty soon. Like this is getting a bit much, but yeah. That's how reviewing goes sometimes. So suppose we had a plane here. Suppose we had a plane like this. And we had some vector, okay, I should probably use like a different color. We had some vector A like this. And then we had like another vector all the way over here like this. Right, so here we would need to like find a basis for this plane, right? In our previous example before, when we were projecting onto a single line, right, and that was fine, but now we need a way to sort of we have 2 vectors now, right? And we have a whole plane, so we need like a basis for the plane. So we need 2 vectors that make a basis for this plane, and then we can project onto the plane. And so P, right, P would be equal to A1x1, right? Same thing as before, right? The projection portion is like A1x1, right, plus like A2, like this guy over here is like A2, right? A2, and this is A1, plus A2x2. Okay, and so you're looking for a linear combination of the basis vectors. That's what's going to give you like the whole plane, right? And we spoke about this before. It's like you need like what a basis vector is, and like what is span and independence and dimension, all of that. So this, we can actually just put it into the columns of a matrix A, because we're doing linear algebra here. And so we can say this is A1, and oops, we can say this is A2. And then we can just take our vector x and put it outside here, like so. And it's the same linear combination, really. It's just written in matrix form, right? So this is in a column of a matrix times x hat. So therefore, right, P is equal to ax hat, right? And that's a linear combination of the basis vector. So I suppose I should write that. So P is equal to a x hat. So that's our linear combination of basis vectors. But that's how we describe the plane, right? Yeah. Okay, so I think I'm gonna take a little break here. I need more water. I need to use the restroom as well. Also getting very hungry, so I'll be right back. Alright, so we're back. Okay, so we were talking about a basis for the plane, describing the plane. And so now we need to find what linear combination is perpendicular to the plane, because remember, we're projecting onto the plane. And so we said that this error vector is b minus p, right? In this case, p is just ax hat. And so let me just say our error vector e is b minus ax hat. Right, this is just like a generalization now from our previous example, right? So therefore, what we're solving for is A1 transpose, because we know, right, A1 transpose, you should be able to see this, A1 transpose times E, times E. I'm not gonna like write the whole thing out now because like, come on, is equal to 0, right? Right, so that's for the first basis vector, right? But we have an entire plane now, right? Or we can even go, once we have two vectors, we can go like the n-dimensional space now. So it doesn't matter. And then we have our next basis vector, A2 transpose E, and you're just substituting this in place of E, but I'm just too like lazy to type it out or write it out here because my touchpad is like killing me. But okay, we can put A transpose into a matrix, right? So we can turn this into a system, right? This is linear algebra. That's what we do. We make systems here. So we can say, okay, well, let's just put A transpose into the columns of a matrix. So we can have like A1 transpose up here, and we can have A2 transpose down here, right? And then this is multiplying your error vector E. Okay, it's actually B minus AX hat, but I'm just not going to write it out, right? And then this produces your 0 vector, right? Like so. And then, okay, well now you can just turn this into capital A, right? So your equation now becomes, so this is just one matrix really, so this is now just A transpose. And I suppose now for the final thing I'll just write it out, A transpose B minus AX hat is equal to 0. Okay, and then you do quite literally the same thing. You expand out and you solve for x hat. Okay, and oh, but like there's something really and this is where like it's like super useful to like know them. Like if something, right, your error vector, remember this is your error vector. Your error vector is in what? It's in the null space of A transpose. That means it's what? It's perpendicular to the column space of A. Yes! Like, exactly. That's the whole point. The whole point was to show that the error vector is, like, in fact, perpendicular to your column space, right? In this case, your basis for your two basis vectors. That's what formed your column space. So, like, yeah, exactly. You know? And then, so you can just, like, A transpose B minus A transpose AX is equal to 0, and then you can do a bit of reordering and you'll get A transpose A X bar is equal to A transpose B. Like, I'm just like working out like if you were to FOIL this out, right? And so okay, so let me just like do it out. So the final thing, right, more towards the end, will be A transpose A X bar is equal to A transpose B. This is our magic formula here. And so the point is, right, if you can't solve AX equals B, you can make the matrix symmetric by multiplying both sides by A transpose. Do you see that? Like we had an AX over here, right? AX equals B, but then we just left multiplied by A transpose. So A transpose A, so we've made a symmetric matrix is equal to A transpose B. Like, I hope you like see what's going on there. Like, and you can like FOIL this out and see that you'll end up with this as well. And it's just so nice to see. And at least now you have like a proper understanding of what that really means as well, right? And so then you can solve for x now in this particular case. X is just going to be A transpose A inverse, right, times A transpose B, right? So it's just A transpose, well, x hat, I should say. A transpose A inverse. And like we know A transpose A is going to be symmetric, so it's going to have an inverse, and multiplied by A transpose B. And so now we can ask the question, like, what is our projection matrix? Like, it's like sitting right here, like, you know? But you'll see it in a second. So now we know that a P, right? P is equal to A times x, or x hat. So we finally found like what this x hat even is, right? And so p is equal to a times x hat. So this would just be a multiplied by this whole entire thing. But so like out of like laziness, I'm just going to put my a here and like point you up here, right? So this is p, okay? And look at this carefully. Like your projection matrix, right, is acting on some vector b, and it's throwing it down. It's projecting it down into your plane, right? So this here is your, let me put it in red actually. This is your projection matrix right here. This is your projection matrix. You see that this is the thing that's acting on your vector b. Like I hope that point is like clear, you know? So that's your projection matrix. Okay, and then there's like a numerical example. Should I do the numerical example, or should I just like tell you to go watch MIT 1806 lecture 16? Because like, okay, but I do think the numerical example is quite nice. Let me just like review. Maybe it's for my own sake as well. I can review it. Yeah, it looks quite short. And then lecture 17 is on like orthonormal basis vectors, and maybe there's a numerical example here as well for Gram-Schmidt. Now, maybe I'll skip over the numerical example for Gram-Schmidt because, like, I mean, once you see these ideas, then you should be fine, right? So let's do the numerical example here, and it should be good to go. Should I really though? Do I really need this numerical example? I feel like I don't. Like, come on, man. Just go watch like MIT 1806 lecture 16. I'm referring you now to Gilbert Strang, because like this is getting like way too long, and I know how to do it. So, like, I'm not going to like, okay, what just happened there? Insert page after. I'm just going to stick to the core ideas and leave the numerical examples out for later. So the next one was lecture 17, which is like on orthonormal basis. So the chapter starts off with Q transpose Q equals I, right? So that's like the definition of an orthonormal vector. Q transpose Q equals I. And the point is, Q is an orthonormal vector. So what does it mean to be an orthonormal vector? An orthonormal vector is just a vector that's, okay, they're perpendicular and they're also like unit vectors as well. So yeah, exactly. And you can check like Q transpose is I, right? So yeah. Okay, and then there's an example here on length squared as well. Oh, right. So how do you make an orthonormal basis, I think, is the whole point of this chapter. So if you had Qi transpose and Qj, so it's Qi transpose, and then you had Qj here, right? Well, then it's 0, right? If I is not equal to j. Okay, yeah, that makes sense. And it's 1 if I is equal to j. So it's 1 if I is equal to j. Right, exactly. And that this is like Q transpose Q equals I. And you can like take a numerical example. And I'll just like use, I'll just encourage you to work this example on your own, just to like satisfy yourself that if you had like an orthonormal matrix, like you had 0, 1, 0, that's a unit vector, right? And then you had 0, 0, 1, that's another vector that's perpendicular, right? And then you had this one, which is also perpendicular, and it's a basis vector. Then this, you multiply it by its transpose. I'm just going to leave you to transpose this matrix, multiply them. So this is Q, and then you multiply this by Q transpose, and you're going to get the identity back. Okay? You're going to get back the identity. Like somehow, right, the linear combinations of the columns of the matrix transpose, right, produces a diagonal matrix. It's really, really nice. Alright, so x transpose x is just x squared from the Pythagoras example. So, oh right, okay, yeah, fair enough. Oh, so we said before that we had this projection matrix, right? And it was just like these four A's. It was like A times A transpose A inverse A is right. Do you see that? So let's go up back here. Oh, but I kind of ruined. But it was like this. I think it was this portion here. Was it this portion here? Where you had your projection matrix, right? This is our projection matrix, and it's like A times A transpose A, and then A transpose, right? But now, instead of it being like a regular matrix, it's going to have like an orthonormal basis, right? So what you're going to have instead is Q, right? Q transpose Q inverse Q transpose. But something really nice happens here, and this here turns into the identity. Q transpose Q is the identity, right? And the inverse of the identity is just the identity. So you're just left with Q transpose. So your projection is just Q transpose. So like you just like knock this entire portion out entirely. So like you're like optimizing at this point. Oh, my water's finished already. Well, that sucks. And so we said before, right? Then like if you had AX is equal to B, and then you wanted to make the matrix symmetric, and we like saw the entire reasoning behind that, you would get A transpose AX hat is equal to A transpose B. But now if you had an orthonormal basis, right, you would get Q transpose QX is equal to Q transpose B. But again, this just goes, right? And so you're just left with X hat is Q transpose B. So your solution is just like sitting right there in front of you. You know? And so like X hat to the I is like QI transpose times B. And so like the ith component is like it's the ith basis vector times B. Exactly, like it's just sitting there, you know? Like you can see it. So okay, fair enough. And then we go on to Gram-Schmidt. So like how do you get like an orthonormal basis, right? How do you get that? That was the whole point. And then there's like a numerical example as well. Okay, so let's do Gram-Schmidt, the idea of Gram-Schmidt, and then so this is actually just like least squares, by the way. This is a least squares. So the previous numerical example that we skipped over really is least squares. So it's linear regression, right? This is linear regression. It's like some pretty basic machine learning going on here. So, Gram-Schmidt. Well, I shouldn't say basic, but okay. So suppose, right, that we had, again, you could just go watch, take MIT 1806, man. Like, it's so good, okay? It's so good. So we had some vector B here, and we're trying to make an orthonormal basis. So that's the whole point. This is A, this is E. So we're trying to like form our plane as well. God, this drawing is like so terrible. Drawing has never been our strong suit, unfortunately. So we can like have some other vector E here as well. Okay. So how do we get like this to be like perpendicular? How do we turn this vector B into like a perpendicular? First of all, it has to be perpendicular, right, for it to be orthonormal. So we need the ortho, and then we need the normal part, the normalized part. So let's start with the ortho part. Like let's get it orthogonal, like to E. So we start off with B. Capital B is B minus XA. Right, so that this is the error vector, right? I don't know if you remember before, but we know that this error vector here is perpendicular, right? So if we can get this error vector, what we already have like we're done there for B. And here in this particular case, we know X. What is X? X is just A transpose B over A transpose A, right? So I should say this is like capital A in this particular case, if we're dealing like with an entire plane and not just like a single line. But we're already up into n-dimensional space, so it doesn't matter. So X would be let me just write it back. So it's A transpose B over A transpose A. Okay? Oops. Over A transpose A. Yeah, exactly. Right? X is A transpose B over A transpose A. And B is just this is just the arrow vector here, which we know is perpendicular already, right? Because it's sitting in the left null space, so we know it's perpendicular to the column space of A, which we've already gone over before, so it's fine. So therefore, well, what this proves is, okay, insert page after. What this proves is A, right? A, which we just labeled as our first, where is it? Oh no, it's gone somewhere. Oh, here it is. A, right? It's perpendicular to B. It's perpendicular to B, right? By definition, right? Because we just found E, the arrow vector. So this implies that A transpose B, right, is equal to now A transpose, and then you can just substitute in your capital B in this case, which is just B minus XA, right? Well, we know X is A transpose B over A transpose A times A, okay, and it would be 0. So this is just a proof. So this is just A transpose B, really. And yeah, you can like work this out, like do your substitution, remember. So B is just, let me just show you like we have to do. So B is just B minus XA, and then you have to substitute this guy in place of X, and then you can solve, and you'll see that you'll get it equal to 0. So yes, A is in fact perpendicular to B for like 100 different reasons now that we've seen. And so we've got like A, right? A is already like fine, okay? Like the first vector A is fine. We can turn that into like, it's already like perpendicular to itself, if you want to say it. Not really perpendicular to itself, but you need like a starting vector, and then every other vector is going to have to be perpendicular to that. So you might as well pick like A to be like your first vector, and then move from there. And so we have A, we have B, and now what about C? What if we had like a third vector? Now we're ready to go up. But once you have like 3 dimensions, you're ready for like n-dimensional space, right? So we had A here, we have B. What about a third vector here? What if we call this vector like C or E or whatever? Let's call this C. What if we call this vector C? Like how do we do that, right? And so this, you need to like think about it very carefully, but I'll just show you what it is. And so it's, oh, and I'll show you how to normalize the vectors. We haven't normalized these vectors as yet, but it's actually just C divided by, for instance, the length squared. This is what you do. We divide by the length squared, and this is how you normalize to a unit vector, right? Because common A might not be a unit vector, so we need to, like, you know, to get a unit vector in. Okay, so C, how do we get C? So C minus A transpose C, so you'll see exactly what's going on here. A transpose C over A transpose A. So you're subtracting off the projection in this C direction, right? In this C direction. So you're subtracting off that projection, and then you're taking away like the projection in the B component as well. So you're taking away so you're taking away the projection actually in the 8th direction and the B direction, and you're just left with C. Yeah, that makes sense. So it's A minus B transpose C, right, over B transpose B. And this is how you find C. And then obviously you need to normalize, and you're good to go. I think the numerical example is actually quite nice as well. How to find like an orthonormal basis. Pretty nice. Maybe we'll do like the numerical example later on. I just don't want this video to like lag on forever. And so now you know how to make these vectors orthonormal, and don't forget to normalize them. It's just C divided by C. C, the magnitude squared, or in this case it was like A, so it would be like Q. If you're using Q, right, it would just be A over the magnitude of A squared, and then Q2 would be B over the magnitude of B squared, so on and so forth. So, okay, I think that's fine. Now we do, oh god, properties of determinants. Can I just like skip? I'm just gonna skip over determinants because like I know this very well already. I don't think I need to test myself on this. I do think I need to review Gram-Schmidt a little bit because like, okay, let me look at this. Like I understand like this is pretty clear, and here we know we're subtracting off this projection portion in the eighth component, and then in the bth component as well, and then you're just left with the whatever is left back, right? The c direction. So you're like, it makes sense to me. Like, okay, A transpose A, A transpose C for A transpose A. Yeah, this is like the projection in this direction. Like this is the C, and then B transpose C and B transpose A. Like you take off that projection in that direction as well. Yeah. And what you're left with should be perpendicular. If there's like any justice, it should be perpendicular to like both of these vectors as well. So that makes sense to me. But the numerical example, like this might seem a little bit abstract, but I think once you do the numerical example, you do see like it just comes together nicely. So perhaps I'll do the numerical example later on just to satisfy myself that this is in fact true, right? And we're gonna skip over properties of determinants, but there's like 10 axioms that you need to go over to understand quite a bit of stuff. And let me see. Yeah, there's determinant factors and cofactors, formulas and cofactors rather. And then there's a numerical example, which I don't think I need to do at the moment. Like I'm pretty confident I know how to do cofactor expansion. Come on. And then there's like Kramer's rule, which like you do need to understand like the previous two lectures to like really see what Kramer's rule is about, and it does come in helpful as well. Like at least algebraically, numerically it's a nightmare, but algebraically it's okay. So it does offer you value in that sense, right? And so I'm just going to skip over this entire part, and then yeah, there's this portion on volume, right? Yeah. So yeah, determinants really do give you a great way to think about the volume of something, and then yeah, you can actually work backwards and prove the 10 axioms from volume itself. So it just, yeah, they imply each other in a sense. Okay, and so I'm just gonna go straight to, I'm gonna try and run through eigenvalues and eigenvectors, and maybe touch a little bit on Markov matrices, trying to avoid too many examples because this has certainly gone on for far too long. But I'm certainly very, very happy so far, and so I'm just going to like speed run this eigenvector chapter because I just know this so well already, so I don't really need to satisfy myself here. But just for like the sake of completeness, and I did promise somebody that I would like compute the 2000 Fibonacci number, so maybe we can just like skip to that part and just compute the 2000 Fibonacci number and just don't be bothered with explaining anything. I think that's perfectly perfectly normal. So yeah, we're actually just gonna do that. So this is our system. So let's do it. I just want to put it into this. So computing the 2000 Fibonacci number. This is our goal. Whoops, can't even plug computing. That's fine. So u to the k. I think the system is u to the k is equal to, and this is how you compute high powers of a matrix, by the way. So this is a to the k u naught, a to the k u naught. So this is your initial vector u naught here, and we need to first of all understand what the Fibonacci sequence is. And so it's like 0, 1, 1, and then 2, and then 3, and then 5, and then 8, and so on and so forth. And so you can see then that this 8, for instance, is the sum of the two previous values, right? And this 3 is the sum of the two previous values, and so on. Like, that's how the sequence goes, right? And so your initial vector then is, so let me write the initial vector. Your initial vector in the system, u0, initial vector, is just fk plus 1 plus 1 and fk, right? This is your initial vector, and your system is actually defined as fk plus, yeah, it's fk plus 1, fk plus 2. It's pretty simple, right? So it's fk, like I just showed you this. It's like fk plus fk plus 1 is like equal to fk plus 2, right? Like, I hope you can see, like, this is what, like, algebraically what the Fibonacci sequence looks like. So fk, your some kth value is just like some k plus 2 value. So like here 8, right? It's just the sum of fk plus 1 plus fk. Like that should be clear. But this is not enough because this is linear algebra. We need a system. We need to artificially create a system. And so we can just come at the bottom here and just do something like really seemingly dumb, but it's actually like quite a clever trick. So fk plus 1 is just equal to fk plus 1. So we've like just like, there we go. And so what we can do is that we can just now throw this into our matrix A, right? We can call this A, and like linear algebra just takes over at this point. And so your matrix of coefficients is just 1, 1, 1, 0. I hope you can see that, right? Just one of this, one of this, one of this, and there's nothing here, right? So u to the k is equal to A times uk. So this is our initial vector here. Just u to the k, uk. Okay, so I hope that's clear. This should not be u naught. This would be u to the k in general. U naught would actually just be 0 and 1. So, okay, and so now what we have to do is compute the eigenvectors and the eigenvalues of this matrix, which is fairly simple. I really should explain what diagonalization is. Do I really want to? Oh god, I don't want to. Like, this video has gone on forever. I just want to compute this thing and like maybe touch on Markov matrices and just get out of here. We'll do the rest later on. We'll do the rest like sometime during the semester, like when we actually get there. Okay, so the characteristic equation we need to solve first of all is a minus lambda I. So a minus lambda I, right? And so this, I'm not even going to write it out. The solution to this is just lambda squared. So this is just like the matrix A shifted by lambda, right? So shifted by lambda I. So it's like subtracting off lambda from the diagonals, really. So it's lambda squared minus lambda minus 1 is equal to 0. And this is your characteristic polynomial. It's not too difficult to solve. You can just like get this done with like use your quadratic equation if you wanted to, and so you can just get lambda is equal to 1 plus or minus a square root of 5, right? And so lambda 1 would just be 1 plus or plus square root of 5, right? I think this is fine. Let's see. Where did I compute the inverse? Right, so it's 1 plus the square root of 5 over 2. I'm gonna use it in this form because I think it's nicer. And then lambda 2 is 1 minus the square root of 5 over 2. So 1 minus square root of 5 over 2. Okay, so this is your lambda 1, lambda 2. You can like solve this with like quadratic equation if you wanted to. It's just 1 plus or minus square root of 5 over 2. It's nothing difficult. So let's go to the next page. So the page after. So we have lambda 1, lambda 2, right? Now we need, what do we need? Do we need the eigenvectors? Yes, we do need the eigenvectors. So the eigenvectors for this system is simply, you're plugging the lambdas back into the original equation that you simply cannot solve. Let me just write that equation down in case you don't know what it is. So it's just a minus lambda I x equals 0, and this is just a null space equation that you're solving. We're already familiar with the null space. So we have lambda now, so we can solve for x, which was the problem initially. You can't solve for x. And this, by the way, comes from, I'm just going to tell you very quickly, this comes from ax equals to lambda x, which gives you the definition of what an eigenvalue and an eigenvector is, right? It's just some vector x when acted on a system A, right? That vector comes out parallel to itself, right? And the lambda, or the eigenvalues, is just like some stretching value, right? So it could be negative as well. Right, so some linear combination of the columns of A, but that linear combination itself you get back on the other side, but like, you know, stretched by some scalar factor called lambda, and that is considered your eigenvector, and the lambda would be your eigenvalues. And then you get this here that you can't solve because you have two unknowns. You have lambda and you have x, but we know then that the matrix is singular, right? We know the matrix is singular because it's a null space matrix, right? So there's something in the null space of this matrix. So if it's singular, we know the determinant of a singular matrix is 0, so that's what we solved up there. So that's how we got the lambda. So now you plug this back in here and you find the eigenvectors, which I'm not going to do. You can do that if you know how to solve this now, right? You can eliminate if you want to, find your pivot variables, your pivot columns rather, find your free columns, and then you get your null space bases. You can even put it into reduced row echelon form and then read off the negative f and the I if you wanted to. However you want to solve this, it's up to you. But you can like take gospel truth that x1 is equal to lambda 1, 1, and x2 is lambda 2. And you can like check it right here to x2 is lambda 2, 2. And we already know what lambda 1 and lambda 2 are, so you can like plug it in and check if you want to. Like you can plug this into this system here and you'll see that it comes out to 0, and this one as well. So they both satisfy this condition. Okay. Now, high powers of a matrix. Let me just like briefly touch on this. So let me see. Do I have notes on this? I think I might have notes. I don't even need the notes. I don't need the notes. I don't know where it is, but I don't need it. So we know AS. A times S. So what is S, right? So S is this eigenvector matrix. So we just found two eigenvectors, right? We found x1 as an eigenvector and we found x2 as an eigenvector. We put that into a matrix S. By the way, we need like n independent eigenvectors because we're going to have to invert S. You'll see later on. So if we don't have independent eigenvectors, we can't invert S, and none of this works. So it's very important. Because like if you do have like a repeated lambda, for instance, then you might like end up with a degenerate system, really, and you couldn't invert. So okay, AS is equal to what, right? AS is equal to A times, we just said S is just this eigenvector matrix, right? So x1, x2, all the way to xn, right? So we just take the eigenvectors that we compute and we put them into a matrix, call it S, right? So this is what we're dealing with here. Now we know that AX is equal to lambda x. That's the definition of, that's like the whole thing, right? That's where the characteristic equation comes from. And so we know AX1, we can just rewrite that as lambda 1 x1, lambda 2 x2, all the way up to, oh god, yeah, lambda 2 x2, all the way up to lambda n xn, right? Now here is where you just get matrix multiplication just working for you. You can diagonalize this matrix. What does that mean? It means that you can actually take these lambdas and put them on a diagonal matrix and multiply it by the original eigenvector matrix. And so what you end up with is, and you'll see why this is really, really nice. What you end up with here is, you end up with x1 back, x2 back, all the way to xn, right? So this is your matrix S that we started with, right? This is your eigenvector matrix. Now, how do I get this back? Like, can you think for a second how you might get that back? Well, if you think about this carefully, right? If you have, like, how do I get back this particular entry here? Well, you just put lambda 1 on this first entry and you just get zeros all below it. What is this saying? Like, as linear combinations of column, what is it saying? It's saying one of the first column and none of the others, right, is going to give me this value here. And then if I come over here and put a 0 here and put a lambda 1 and lambda 2 here, it's going to, okay, give me 0 of this guy, 1 of the second one, none of the others, I'm going to get back this entry here. And so you can see we just end up with lambda sitting on the diagonal here and zeros everywhere else. And this matrix we call capital lambda, right? So we've shown that A times S is just S lambda. And now we can say A is equal to S lambda S inverse, and this is a very important factorization because it allows us to think about high powers of a matrix. And so A to the squared, right, would be what? A, look at this now, A lambda S inverse S lambda S inverse. What happens here? This is gone, right? And so A squared is simply S lambda to the S lambda squared S inverse. And so A to the k, right, in general, because you can imagine if we had like k of these together, like these s's would just keep turning into identities. So we just get A to the k is just S lambda to the k S inverse. Like this. S inverse. I don't know why I have a square there, but this is supposed to be an inverse. Okay, look at this. This is so nice. So now, like the only thing that's like we couldn't do this before. Like if we did like QR factorization or LU factorization, we couldn't do this. Like this is like such an important factorization. And then later on, you'll come to learn that there's like Q lambda Q inverse, like which is like so nice. But okay, like I'm getting like way ahead of myself here, but point being, like if you're raising a matrix to really really high powers, right, what's gonna happen is that the the lambdas are the only thing that's like changing. The s and the s inverse is like not changing at all, you know. And then there's this notion of steady state as well. Like if the lambdas inside of this system, right, were less than 1, right, and you started taking higher and higher powers of this matrix, what's going to happen? It's gonna go to 0, right? It's gonna go to, like if you had 0.5 and then like you square that, what's gonna happen? It's gonna get smaller and smaller and smaller the more you square it, and it's gonna tend towards 0. It's like as k tends to infinity, right, this lambda is gonna go down and down and down, and so that's how you get like steady states and stuff. So like steady state here would be like 1, for instance. In the case of Markov matrices, your steady state would, like your leading coefficient would be lambda equals 1. And you kind of need to see this, like what do I mean by leading coefficient? It's actually this thing here. Where is it? This guy here. Remember, this is the same thing, right? And this is your leading coefficient here. And so if you can imagine this was like lambda equal 1, right? And then all of these values were less than 1, they would all go to 0, and you would just be left with this guy here. Okay, but that's just like a little brief introduction to eigenvalues, eigenvectors. Let me continue with my Fibonacci example. I sort of lost my train of thought for a bit as well. So we computed lambda 1, lambda 2, and we computed the eigenvectors as well, I believe. Where are they? Oh my god, like where is my... Oh no, don't tell me I lost my eigenvectors that I computed. Is it over here? Like how do I... Okay, no, it's not over there. Hang on a second, I need to find where my... Okay, so we have lambda 1, lambda 2. That's the eigenvalues. I don't know where the eigenvectors are though. Maybe they're over here somewhere. Yeah, right? Yeah, so the eigenvectors was just lambda 1, 1 and lambda 2, 2. And so we have the eigenvalues, we have the eigenvectors. Do we have enough? We need S inverse now, right? So we knew that, okay, so we know that u to the k, right? In this particular case, we're computing u to the 2000. We want to know what happens after 2000 steps, right? Would just be our matrix A, which we can now say is S lambda S inverse, right? Times our initial vector, right? Our initial vector, by the way, is just fk plus 1. So fk is 0 and fk plus 1 is 1. So this is the initial vector, right? And so we need this inverse. So where is... How do we get... So you could compute the inverse with Gaussian elimination. In this case, computationally, it would be very fast, but for us, algebraically, it might be a bit of a headache. And so this is probably the part where I regret skipping over not the determinant section. But okay, you should know the determinant of a 2 by 2 is just 1... Oh, sorry, the inverse of a 2 by 2 is just 1 over the determinant. So AD minus BC multiplied by this cofactor matrix transposed, right? So it's not the cofactor matrix, it's the cofactor matrix transposed. So you end up with minus C minus B, A and D here. So what does this amount to? Well, this is just 1 over the square root of 5. Oops. And it's times 1, negative 1. And lambda 2 was square root of 5. What was lambda 2? No, it's negative lambda, so negative lambda 2. So square root of 5 minus 1, I think. Over 2, and this guy was 1 plus square root of 5 over 2. Question here is though, is there a negative sign somewhere here that I need to like be looking out for? Because it's negative lambda 2, not just like lambda 2 by itself. So what is lambda 2 though? Okay, we're just gonna do the computation and we're gonna see. Oh, it actually never matters, but this actually is supposed to be negative lambda 2, but it never matters because of the initial condition that's applied. So let's go back to what we're solving here, right? So it's this initial vector u0 times this matrix, right, which is 1 and 0 times this matrix. And so what actually happens is that we're taking none of the second component, so this is gone. The lambdas are just gone, and we're just taking one of this component here. So the lambdas actually didn't even factor into this equation at all, because we're taking no linear combinations of that column. So what we end up with actually is just this guy, 1 over square root of 5, and negative 1 over square root of 5. I hope you can see like how that happened. Like we're just taking one of this column, and we have this governing scalar outside that we need to distribute inside as well. So this here, what we just computed would be this guy here, S inverse times this guy. Now we need to compute lambda to the 2000, and then we need to multiply it by the matrix S, and we should be good to go. So let me open up matrix calculator, which I have ready, and so the first thing we need to put in is this guy, 1 over the square root of 5, and it's negative 1 over the square root of 5. Should be good. No, it's complaining for some reason. Stop complaining. Negative 1 over square root of 5. Okay, stop complaining. And over here, we need to multiply this by, I think it was lambda to the 2000, right? So we have this here. Now we need to do lambda to the 2000. We know lambda is just this diagonal matrix with lambda 1 here and lambda 2 here. Remember I showed you earlier where that came from. And so lambda 1 is 1 plus the square root of 5 over 2. So this is just 1 plus the square root of 5 over 2, and then it's like all raised to the 2000th power. Is that okay? It's complaining for some reason. Okay, let me write it back. Like, let's see. Oops. So it's put this in square brackets. So we'll say 1 plus the square root of 5. 1 plus the square root of 5 divided by 2, and then this entire thing needs to be raised to the 2000th power. I don't see why that's a problem. Okay, it's not. Isn't that exactly what I wrote like a second ago? I don't know. And then lambda 2 is like the same thing, but it's 1 minus, right? Or is it like the square root of 5 minus 1, which is like the same thing, right? Yeah, it's like 1 minus the square. Okay, so it doesn't matter. Let's just put it. So it's, put this in brackets, square root of 5 minus 1 divided by 2. And then let's cover this in parentheses. Raised to the 2000 power. Okay, so this times this. Okay, double check. I think we're good. So we get this guy here. So now we've completed this portion of the calculation as well, and so now we just need to multiply the result times this matrix S. So I can go like collect this, like insert this in B, and then for the matrix S, I believe it was lambda 1 1, right? Was that our matrix S? What was our matrix S again? First of all, what are the eigenvalues, and then we can just get the matrix S from the eigenvalues. Where are our eigenvalues? Oh no, I'm not sure if it's lambda 1 1, lambda 2 1. It might be, but I have to double check. Where are you? Eigenvalues that we took our time to compute. Where are they? Oh yeah, so lambda 1 1, lambda 2 2. Lambda 2 1 rather. So lambda, is this lambda 1? Yeah, so this is lambda 1 1. And then lambda 2 1 comes here. Lambda 2 1 comes here. And so this should be, if there's any justice, the 2000 Fibonacci number should be sitting somewhere. This doesn't look right at all. Oh god, no, of course it's not right, because we still have this raised to the 2000th power, so of course not. So let's do A times B, and we should get the right answer. Yeah, this is it. This is the 2000 Fibonacci number. How do I know? Because I've computed this before. Haha. So, but you can go Google like what the 2000 Fibonacci number is, and you'll see like it's exactly this here. And it ends in 25 because I know I checked that. Like, yeah, there it is. It ends in 25. Okay, so there we go. 2000 Fibonacci number. Now maybe I should just touch briefly on Markov matrices. What is a Markov matrices? All entities of the matrix, right? So I'm just gonna talk now. So it's just like all entities of the matrix greater than or equal to 0. And so the sum down the columns add up to 1. So you can imagine you can have like 0.1, 0.2, 0.7, right? Being a column of the matrix, and they all add to 1. And so Markov matrices or stochastic matrices really is, they represent probability distributions, really. And so this is a fun fact. Squaring the matrix, right, is going to give you another Markov matrix. So the powers of a Markov matrix is themselves a Markov matrix, and the lambda equals 1 is like the steady state of this matrix. And note as well, the lambda equals 1 is an eigenvalue, right? And why is that? Because you know that if you sum down the columns, like this is a, what can I say, a criteria for being a Markov matrix. Like summing down the diagonals give you 1. Like we know what that is, right? That's the row space or the column space of A transpose. There's something in the column space of A transpose, I guess is what I'm trying to say. So that means that your matrix is in fact singular as well, if there's something in the column space of A transpose. So that's how you know like eigenvalue 1 is like always there, and you can check it, right? And okay, yeah. So you can do like A minus 1 lambda, right? You can find the determinant of A minus 1 lambda 1i rather, and you can like see that it like gives you 0, so you're good to go. Okay, was there anything else? No. And then you just do like a numerical example. From there you already know how to find the lambdas and the eigenvectors, so you can just apply high powers of a matrix now. And so you can have like some values that represent maybe population movements from, I think the example he used was from Massachusetts to California, right? And you can see, okay, what happens after 5 years, after some like probability values that you have inside of the matrix, or what's going to happen after 10 years, for instance, yeah, something like that. And so yeah, you can use these to like predict a lot of things. You can predict weather. It's used in robotics, because remember, the information inside of your sensors is not always perfect, but like there's some probability there, right? And so you need to find like, okay, if we run this after, I don't know, run this infinitely many times, then it's going to reach a steady state, and you can make like a pretty reasonable prediction from there. Or even like if you want to know like a finite number of steps, like what happens after 100 years, then you can see, okay, compute a to the 100, and it would just be u to the 100 is a to the 100 u naught, and you've already seen how to do that here. Okay, so I think I've covered like a pretty good amount of linear algebra. I think at least we must have covered at least 24 lectures. I think from here there's like a couple lectures on symmetric matrices, which is like fairly easy to follow. There's singular value decomposition. There's a lecture I think on the Fourier series and the Fourier transform, fast Fourier transform actually, which actually changed a lot of things. And yeah, it's like crazy amount of like optimization that went on there. And I think there's linear transformation. Ironically, linear transformations comes at the end of the course. Usually, you see that at the beginning of like a linear algebra course, right? It just comes at the end of the course, which is nice. And then there's like change of basis, and an example on image compression, I think. So yeah, I think we're sitting pretty okay for linear algebra. Maybe in the future you'll see me making some terrible French videos, because I have French the entire year. So we'll see how that goes. All right, peace.